Good evening to all. Confirm. So voice is clear. Screen and all are clear, right? Right. So I'll be discussing today's class. So today is day 8. Date is 13/07/2021. Right. So I'll proceed with today's class, all of you. So I voice will a little bit come out. Don't worry, right? So the voice will come out. Now it is clear, all of you. Right. So I'll start the class. I'll start the class now. Right. See, what is that means? The phasor diagram. So I'll be drawing the phasor diagram to know the load angle. So what is that load angle means? I told you yesterday, basing on the load on the motor, the relative speed between the stator field and the rotor field will be there. Why? Because if the load is very light, then the relative speed between the stator field and the rotor conductors will be very less. So that the rotor conductors are very closer to the field, the relative speed is less, flux cuttings is less, EMF will be less, currents will be less, right? But with the increase in the load angle or the relative speed has to increase. So what is this load angle in case of induction motor? So anyone knows the load angle for induction motor? Can you please give the answer? If you can please, right? Sai Charan Reddy, you are supposed to ask the question, okay? See, yesterday you are not there, right? I appreciate your questions and please try to ask the question. Sai Charan Reddy. I hope please. Are a few. Right. Done. So today's class also we'll try to see. Fine. So we'll see what is called as load angle. So if I want to explain the concept of this load angle, first of all, you should know what is called as a phasor. What is a phasor? Means it is a moving vector or rotating vector. What do you mean by that? See, if we just recall the circuits, I'm not talking about in detail concept about the phasors. So if I take the concept of phasors now, I'll take more than 2-3 hours for that. So that is not required for your induction. I'll take very little which is required for us. So if you take a AC voltage and I'm taking a pure inductor. So this is voltage and this is a pure inductor. So when I'm giving a pure AC to an inductor, then you know that the current lags the voltage by an angle 90 degrees. So if I'm trying to represent the same thing with a sinusoidal, so if I'm calling this one as a voltage V of t, so this is the voltage V of t, then the current through this inductor will lag by an angle 90 degrees. Will lag by an angle 90 degrees. Don't ask now how, so you can see everything in your circuits. You can see with respect to time, the angle between those two peaks will be always 90 degrees. So this is something like a sinusoidal representation of the voltage across and current through inductors. You can see the time angle between those two can be 90 degrees. Is it clear? Confirm me. Is it clear? Confirm me. Yes. Now the same sinusoids can be represented like a moving phasor. So I'm not trying to draw the phasors. So I'm trying to represent the moving phasor. So if I'm trying to represent this voltage as V, then with respect to that current lags by an angle 90 degrees. So I'm representing like phasor. The same sinusoids I'm representing like a phasor. So whatever the time angle we are having between those two peaks, that's sinusoidal. So this voltage sinusoid is represented with a phasor, and this current sinusoid is represented with a phasor, and the angle between those two peaks is 90 degrees, right? So the same sinusoidal representation between voltage and current can be represented with the help of a phasor. How your network teacher will explain. So I think you know the difference between a sinusoidal representation and a phasor representation. You can see that sinusoidal representation of voltage and current with a time angle of 90 degrees, we are representing with a phasor with a time angle of 90 degrees. Is it clear? Confirm me all of you. Confirm me all of you. Right. Now, whatever the concepts which we have discussed in induction machine, the sinusoidal representation, you know that the MMF wave is a sinusoid which is moving in space with a speed of 120 F by P. The voltage which is induced in the windings is a sinusoidal voltage. The currents which are passing through that conductors is a sinusoidal voltage. So everything are something like sinusoidal. So I can represent those sinusoidal waveforms or sinusoidal quantities like a phasor quantities. Why? Because by looking into the phasor, we can imagine so the time angles and other things. So whatever the sinusoidals we have seen, a three-phase MMF, resultant MMF, the voltage induced in the windings, the currents flowing in the windings. So all those are sinusoids. I can represent those sinusoids like a phasors. That we call it as a phasor diagram. So the sinusoidals can be represented like a phasors, right? So I'm trying to draw the phasor diagram for an induction motor. I hope you understood the difference between a sinusoid and a phasor. Is it clear? Confirm me. Is it clear? Confirm me, all of you. Right. Done. So by the way, what is the load angle? So load angle means it is the spatial angle. It is the spatial angle between the resultant field and the rotor field. So the spatial angle between the resultant field and the rotor field, right? I can show the same thing like a sinusoidal, but it is very typical to understand what is that. See, the MMF wave will be moving in space, traveling in space with a peak value of 3 by 2 times of Fm. Then this will produce as a flux. This flux will cut the conductors and hence an EMF is induced. That EMF will lag by an angle 90 degrees. If the current is there, that current will lag by some angle. So all these are something like a sinusoidal representation, which is something like complicated. So instead of representing those sinusoids of flux, EMF, current, I'll be representing those sinusoids as phasors, right? So I hope you understood the difference between a phasor and a sinusoid, right? So whenever I'm trying to draw the phasor diagram, please remember that I need to take the reference. So here the reference is the stator, and with respect to that stator, if you remember, the resultant field, the resultant flux will be rotating with a speed of ns is equal to 120 into f by p. So the resultant MMF is a sinusoidal MMF. I hope you remember. So already you have drawn. It is a sinusoidal MMF. That sinusoidal MMF I am representing like a phasor. So with respect to space, the resultant MMF phi r is rotating with a speed of ns. Is rotating with a speed of ns. If you remember, already I told you. So this is the MMF wave. So with respect to space, this MMF is moving with a peak value of 3 by 2 times of Fm. That sinusoidal I'm representing like a phasor now. So that phasor is a quantity length represent the magnitude, right? So what is the magnitude? It is 3 by 2 times of phi m, and it rotates with a speed of ns. So that I have represented like a phasor. Is this point clear? Is this point clear? Confirm me. Right. Now, as this flux cuts the stator conductors on the rotor conductors, as these flux lines cuts the stator conductors and the rotor conductors, what is induced in both the windings? An EMF is induced. Already you have seen the theory. As this flux cuts the stator conductors and rotor conductors, what is induced in that? An EMF will be induced. Whatever the EMF that is induced is a sinusoidal voltage, Again, that sinusoidal voltage can be represented like a phasor. That means the EMF E1, which is induced in the stator winding, the EMF E2, which is induced in the rotor winding, I show like a phasor. That sinusoidal EMF, I show it like a phasor. If you remember, the relationship between the flux and the induced EMF, the angle between the flux and the induced EMF will be 90 degrees. Why? Because, so if I take this flux as phi m sin omega t, the induced EMF is equal to minus n into d phi by dt. If I simplify this, so n phi m omega, I'll get sine omega t minus 90. If you just remember that, sine omega t minus 90. So with respect to that flux, the EMF will lag by an angle 90 degrees. So whatever the EMF that is induced will lag by an angle 90 degrees. So with respect to this resultant, so that EMF will lag by an angle 90 degrees. Again, that EMF is a sinusoid, and I'm representing that sinusoid as a phasor. So this is E1. And the same flux lines are cutting the rotor conductors, and even an EMF is induced in the rotor conductors. Even that EMF will also lag by an angle 90 degrees. By an angle 90 degrees. Then you may have a doubt, sir, why you have drawn the length of the phasor E1 as more, the length of the phasor E2 as a less. So you mean to say that the EMF induced in the stator winding is more compared to the EMF induced in the rotor winding? Yes. Why, sir? Why? Because if you remember, the stator conductors are stationary and this field is rotating with a speed of ns. What is the relative speed between the field and the stator conductors? Ns minus 0, it is ns. So the flux cuttings will be more, the EMFs will be more, the currents, the magnitude of EMFs will be more. But what is the relative speed between the stator field and the rotor conductors? Ns minus nr. The relative speed is less. The flux cutting the rotor conductors will be less. EMF will be less. So that is the reason the magnitude of E1 I have drawn like a lengthy, and E2 I have drawn as a small phasor. Is it clear? Is it clear? Is it clear, all of you? Right. Now, I'll be assuming that rotor circuit is RL circuit. Why? Immediately after this, we'll discuss immediately. If the rotor circuit is RL circuit, then whatever the current that circulates will lag by an angle theta 2. Whatever the current that lags by an angle theta 2. And you know that this rotor current is also sinusoidal. Already I have drawn sinusoidal current. Sinusoidal current. So whatever the flux that produce due to that current is N I by reluctance. So N by reluctance is a constant. So the phase of phi 2 and the phase of I will be same. So if I'm calling this one as a rotor current, then whatever the flux that is produced due to that rotor currents, we have seen the secondary field, the rotor field. It is also sinusoidally varying, that can be represented like another phasor. And what is the phase of I2 and phi 2 means the phase of phi 2 and I2 will be same. So with respect to this phi 2, definitely there is one flux. Even that flux with respect to stator, it is rotating with a space with a speed of ns is equal to 120 f by p. Already we have seen the speed of the resultant field, the speed of the stator field, the speed of the rotor field with respect to stator is ns. I have drawn this. So this angle is 90, and I told you that the spatial angle between the resultant field and the rotor field is called as the load angle. So what is the resultant angle here? You can see the angle between these two is 90 plus theta 2, and this angle we call it as a load angle, and generally we represent that load angle with delta, right? So if I want to find out the load angle, I need to draw the phasors of resultant field, EMF, rotor current, and rotor flux. The same thing can be represented by a sinusoidal waveform, but that will give something like typical to understand. That is the reason those sinusoidal I'm representing like a phasor. So these phasors can give a easy way of understanding. So from that we can find out this load angle. Then what is the load angle between the resultant field and the rotor field? It is 90 plus theta 2. So this is the load angle. Is it clear? Confirm me. Confirm me. Once again, I'm just I'm revising or recapping. What is it, Baba? I want to find out the spatial angle between the resultant field and the rotor field. So those are something like sinusoidal quantities which are varying in space, but it is very difficult. I can draw, it is not a big deal. So those sinusoidal quantities, if I want to represent, then it may be something difficult, but the circuit has provided a easy solution for that. What is that easy solution? The same sinusoids can be represented as a phasors. The best example is, if you recall, in case of a pure inductor, the current lacks the voltage by an angle 90. So those voltages and currents which are sinusoids can be represented. The same thing can be represented like a phasor. That with that concept, I'm representing this sinusoidally varying quantity, resultant field, rotor, EMF stator, EMF, rotor current, like a phasor. So this is the phasor diagram. So finally, what is the spatial angle we are having between the resultant field and the rotor field is 90 plus theta 2, and that we call it as a load angle. So tomorrow, if anyone questions you what is a load angle, so the load angle for an induction motor is 90 plus theta 2. Why? Because which is the field that is responsible for rotating the rotor resultant. So from that, this rotor field is coming back. Why the rotor field is coming back? Because of the load on the motor. So that angle we call it as a load angle. Is it clear? Confirm me. Right. So this is for motor. This is for motor. But as of now, I'll give it for generator also with a small logic. Then I can just give it for generator also, small logic. What is that? If I'm taking a series motor, series machine, that's which is small logic I'm trying to give. Series machine. So if I'm giving an excitation to this machine, if this machine is acting as a motor, then it will draw the current from the source. It draw the current from the source. But if the same machine, if it is acting as a generator, then it will supply the current into the load. Then what is the angle between those two currents? They are like facing opposite. The angle is 180 degrees. On the same lines, if I2 is the motor current, then what will be the generator current? Means the generator current will be like this. So this will be the generator current. I'm drawing roughly smaller value, generator current. So because of this generator, there is one flux, and this is theta 2, opposite angles, theta 2, and this angle will be 90 minus theta 2. 90 minus theta 2. So what is the load angle for induction generator? Means 90 minus theta 2. What is the load angle for induction motor? Means 90 plus theta 2, right? So can I write finally the spatial angle, angle between the resultant field axis and the rotor field axis is called the load angle. It is 90 plus theta 2 for induction motors and 90 minus theta 2 for induction generators. Where theta 2 is the rotor power factor angle. I hope this point is clear. All of you confirm with me. Right. Only few. What happens to others? Raise the hands, all of you. So basing on this, in the previous gate, there was a question for 2 marks. What is that question means? See, please get ready for the answers, all of you. The rotor power factor of a 3-phase induction motor is 0.866 lagging. what is the spatial angle between the resultant field and rotor field? Option A 90, option B 30, option C 120 degrees, option D none. So what is the answer? Can you please give me, all of you? See, why we take E2 and E1 in the same direction? See, Baba, it is not the question in the same direction. Why on the same axis? Why? Because which flux is responsible for E1 and E2? The resultant field only. So with respect to that resultant field, both are lagging by an angle 90 degrees. So with respect to the same quantity, if they are lagging by an angle 90 degrees, then by default, they will be on the same phase. So that's the reason I have drawn like a same phase, right? For one. C, 120 degrees. Excellent. Not A, Harshavardhan. C, 120 degrees is correct. 120 degrees is correct. 30 is wrong. Right, 90 plus 30, 120 degrees is correct. So this is enough, right? Don't give the answer, it is, don't type, it is enough. So here cos theta, one second. Cos theta 2 is equal to how much? 0.866. From this, theta 2 is equal to 30 degrees. And the load angle is 90 plus 30, it is 120 degrees. So this is the answer, right? So the answer for this is 30 degrees. 120 degrees. 120 degrees is correct. I hope this is clear. All of you confirm with me. Right, done. Next one is steady state analysis, right? See, I'll work out some examples on this. Don't worry, right? Previous engineering service and get typical questions. I'll take it. Don't worry, I'll do it. The next heading is steady state analysis. Steady state analysis. So if anyone questions you, Araba, what is that you have learned as of now in induction machine? As of now, till this class, till this moment, till this second, whatever it may be. What is that you have learned? Means you can answer the basic laws, the concept of rotating magnetic fields, some main points with respect to induction machines. Then after that, the detailed discussion of construction, and during that the basic requirements for torque production, the pole should be same like that. Then classification of machines basing on the rotor circuit, the complete working principle, the concept of two magnetic fields, the relative speed 0, then the importance of the back EMF. Like that we have learned completely with respect to mostly the theoretical part. Yes. Now the question is, okay, now you have designed one induction motor. Yes, it is with me now. It is with me now. So to that induction motor, I'm giving a 3-phase supply, say 400 volts, 50 hertz supply I'm giving to that motor. Okay. Now the motor is rotating. Yes. I found that it is rotating with a speed of 1440 RPM. Yes. You know that for rotation, for a turning, the rotor has to produce some torque, the twisting effect, the magnitude, the torque. So can you please tell me how to calculate, how to find out the magnitude of the torque which is responsible for turning the rotor and which is making the rotor to rotate with 1440 RPM. So I need to find out what is the magnitude of torque it is developing while it is operating at a speed of 1440 RPM. So do we have any formula? No. As of now, I don't know. As of now, if I want to calculate the torque, I don't know. I don't have any formula at all. Then if you want to calculate what is the magnitude of torque, then you might have learned in your BTech level by conducting a suitable load test, that is by taking a physical motor on input side using that ammeters, voltmeters and wattmeters. On the output side, the mechanical brake drum arrangement, then operating the motor with a particular speed, measuring the output mechanical power, knowing the input electrical power using that watt meters, like that, doing some experiment, taking some values, then doing some calculation on paper, then we can find out the torque, the efficiency, like that we can find out all the mess up. So this is what you might have learned. If anyone asks, can you find out the torque, means I know, but as of now, I know with the help of this mechanical setup, with the help of this load arrangement, I can find out, right? Is it clear? Raise the hands, all of you. Right. But now, without knowing this, without conducting this, even it is possible to know what is the torque it is developing while it is operating with a speed of 1440 RPM, or when it is operating with a speed of some 4%. So without having a physical motor, without conducting a suitable load test, without the measuring equipment, without the brake drum mechanical setup, it is possible to find out the torques, the value of torque. Then how to find out this means we are going to see that in steady state analysis, right? We are going to find out in this steady state analysis, right? So before to that, I'll ask one question. What is that question means? As most of you, the previous machines classes are over, except the batch which is started on July 5th. For other people, the machine classes is over. Other machines are over. Is it clear? Raise the hands, all of you. I'm talking about the old batches. Right. Right. Fine. I'm talking about old batches. Yes. I'll just ask one question and try to give it this answer here. I'm talking about mostly, right? So I'm trying to write only transformer. Yes, if transformer is over, it is enough. So it is enough. Only transformer is finished. Now my question is, what is the equivalent circuit? My question is, what is the equivalent circuit? What do you mean by equivalent circuit? So my question to all, I'm not talking particularly about induction. I'm talking about what is the equivalent circuit. So please try to type it. Right. What is the equivalent circuit? I'm waiting. It is to know performance. Right. Balancing the load, to conduct test. Right. Still representing the loss component, modeling mechanical properties like losses to electrical quantities, representing the machine in electrical parameter. With the help of the equivalent circuit, we can all performance related to machine. Theoretical circuit, very good. So representing a representation of a, elements in a machine. Okay, to convert circuit into a simpler form which will contain no load to full load. Right. Equivalent power circuit. Okay, done. So enough. It is enough. So it is enough. Most of you have given the answers. Enough. Right. Please. Enough. Now don't text. Right. See, what is a equivalent circuit means? An equivalent circuit is nothing but an electrical circuit representation of a physical machine. What is the meaning of a physical machine? Say I'm having a transformer and I'm having an induction machine. I'm having a synchronous machine. So a physical machine can be represented in electrical circuit form. So whatever you want to find out on that particular machine, the same thing can be calculated using this circuit. It is something like a practical experiments you need to conduct to find out. So here, analytical approach, a theoretical approach you can follow to find out the performance. So what is the equivalent circuit means? It is nothing but the electrical circuit representation. If you recall, Electrical circuit means the circuit consists of R, L, C branches connected either in series, parallel or series parallel combination, whatever it may be, the branches will be connected. So what is an equivalent circuit means? It is nothing but a physical machine, a practical machine can be represented on paper in form of a electrical circuit, in form of a electrical circuit. Now the question comes, sir, why we need to represent the machine only in electrical circuit form? Why can't we represent the same machine in other forms? Why? Because among all the calculations, which calculations are simpler and easy means the electrical circuit calculations are simpler and easy. Why? Because if I am correct, in your circuits, you might have used the Ohm's law, the KVL, KCL, the node analysis, mesh analysis, the theorems to find out the response, to find out the current. So using these approaches, we can find out the performance of that circuit. So that is the reason we represent any machine theoretically or for analysis purpose use in the form of a electrical circuit. So can I say what is an equivalent circuit means whatever the machine we have, that machine is represented electrically. Electrically means if you look into a physical machine, you can see a frame, a core, a winding like that. But if you see its equivalent circuit, you find RLC branches. So whatever you want to find out for that machine, you can find out directly on that machine, or if you know the equivalent circuit parameters, you can find out using this equivalent circuit also. If I'm correct, that is the reason your transformer teacher might have represented the complete transformer as a equivalent circuit. Once that equivalent circuit is ready, then using that equivalent circuit, your teacher might have found out the performance parameters like regulation and efficiency. So for finding out the regulation efficiency, no physical machine is given to you, but its equivalent circuit parameters are given. Using that, you're finding out the performance parameter. So 2 points to be noted here. What is an equivalent circuit means? An equivalent circuit is nothing but a physical representation of a electrical circuit representation of a physical machine. Why we need to represent the machine only in electrical circuit form means among all calculation, which calculation are simpler and easy? Circuit, electrical circuit calculations are easy. Then what is that you are going to find out using this equivalent circuit means whatever you want to find out on the machine, the same thing you can find out on this using this equivalent circuit. That means the complete performance parameters can be calculated, can be evaluated using this equivalent circuit. So 3 question, what is an equivalent circuit means? Equivalent circuit is equivalent circuit is a electrical circuit representation of electrical circuit representation of, just once again, it is like electrical circuit representation of, so outside the climate is cool, but just for a closed appearance, just I'm trying to do it. Equivalent circuit representation of a physical machine. Why we need to represent in electrical form? So electrical circuit calculations are simpler. Are simpler. What is that you are going to find out using this equivalent circuit? The complete performance. Complete performance. Complete performance. I hope it is clear. All of you confirm with me. Confirm with me. See, first of all, you should know what is that you are learning. After that, you learn that. Right? Only few remaining. All raise the hands. Right. So first, what I'll try to do means our intention is to find out the performance parameters. That is starting torque, full load torque, maximum torque, like the different parameters I need to find out. But to find out all this, I'm not conducting any load test, but using that equivalent circuit, I'm going to find out. So I need to represent the machine electrically. First, what I'll try to do means, I'll try to represent the rotor circuit first. After that, I'm going to represent the stator circuit. And after that, I'm going to represent the complete equivalent circuit of a induction machine. So which circuit I'm going to represent first means the rotor circuit, right? Rotor equivalent circuit. Rotor circuit I'm trying to represent. A rotor equivalent circuit first. A rotor equivalent circuit. First I'm trying to represent. Right? Now if I want to represent this, you should know some basics of circuits. So you remember that the basic subjects which are very required for all this electrical subject is, the first one is the EMF, the second one is the circuits. Unless and until you have grip or hold on that, so sometimes it may be difficult for you to understand these subjects, right? Anyhow, whenever is required, whatever is required, I'll take and I'll explain, right? So what does it mean by that? So if I'm taking a physical resistor, in other way, the wire wound resistor which you have in the laboratory, I'm taking that. And to that resistor, if I give some power, then what that resistor will do means it will dissipate the power in the form of heat. So that is the reason when you are conducting some experiment in the laboratory, when you are using a variable rheostat, we call it as a rheostat, then if you just go closer to that, if you keep the hand closer to that, you can see there is some heat coming out. Why? Because it is the property that it has to dissipate the power in the form of heat. So there will be some heat coming out, right? Is it clear? Is it clear? Is it clear? Right. So the reverse is also true. What is that? Reverse is also true. If I'm having a conductor or if I'm having a coil, and if I'm passing a current through that conductor or current through the coil, and if I see there is some heat dissipation, then we have to imagine that in that conductor or in that coil there is some resistance property. Because of that there is some heat dissipation. Why? Because unless and until that conductor holds resistance, unless and until that coil holds resistance, there is no heat dissipation. So definitely when there is some heat dissipation coming out of a conductor or a coil which are carrying currents, then I can imagine that there is some resistance inside, there is some opposition for the flow of current inside. So because of that there is some heat dissipation in that conductor or coil. Is it clear? Is it clear? So that is the reason, if I'm correct, while your teacher in power system finding out the performance of the transmission line. So what are the performance of the transmission line? Regulation and efficiency. So the heating effect in the line, is represented with a lumped parameter R. Lumped parameter R. So it is a lumped parameter in short and medium transmission line. Assuming that the parameter is lumped, we find out ohmic losses and we find out the efficiency. We find out the resistive drop and we find out the regulation. So whatever the heating effect we are having throughout the transmission line, so that is shown like a lumped branch R, and with that analysis and with that lumped resistance we are finding out the analysis. So whatever that R you see in the equivalent circuit is not a physical R you are connecting, but the heating effect in the line. Why? Because whenever the transmission lines are carrying current, if there is some heat dissipation coming out, then you can say there is some resistance in that. So that resistance is represented like a lumped parameter for evaluation of short and medium transmission line. But for long transmission line, the results may not be that much appropriate if I'm treating that parameter as a lumped. For that, we take that parameter as a distributed, and basing that, we are trying to do the analysis. Is it clear? Is it clear? Right. Similarly, if I take a pure inductor, then if I give some power to that inductor, it stores the given power in the form of magnetic field. The reverse is also true. If I'm having a conductor, and through that conductor, if I'm passing a current, and if I see there is some magnetism around that conductor or around that coil, then we have to imagine that that coil or that conductor is having inductance. inductive nature. That's the reason there is some magnetism. Otherwise, there is no concept of magnetism. So that is the reason while you are evaluating the performance of the transmission line, the flux or the magnetism effect is represented like a lumped parameter L, and basing on that we are finding out the performance. Similarly, if I take a capacitor, then it stores the given power in the form of electric field. So that is the reason. So between the lines, or between the line and ground in the transmission line, there is some capacitive effect. There is some electric field effect that is represented by a shunt capacitance. And you know that end condenser method, source condenser method, nominal pi, nominal t, we find out all this to find out the performance of the transmission line. So whatever that RLC you are seeing in the transmission line, they are not physically connected, but they are accountable for their properties. That is, when the transmission line is having heat, that is represented by R, when the transmission line is having some magnetic field, that is represented by L, and when that magnetic field, that line is having a electric field, that is represented by C. Is it clear? Confirm me. Confirm me. Right. On the same lines, on the same grounds, I'm going to model. I'm going to model the rotor now. Model rotor. Modeling is nothing but the equivalent circuit. I'm going to model the rotor. So what? How to model? See, whenever we are giving a three-phase excitation to the stator winding, we have seen that magnetic poles are formed, and the nature of these poles are rotating. So they cut the rotor windings and EMF is induced. Then as the rotor circuit is closed, the induced EMF will circulate current. So when those rotor windings are carrying current, then it is observed that there is some heat dissipation. So when there is some heat dissipation, definitely we have to consider that that winding is having some resistance. So that resistance are represented with R suffix 2. So there are two things here. What is that R suffix 2 represent means the rotor winding resistance. It is accountable for, it is responsible for the heating effect in the rotor winding, heating effect in the rotor winding. Then using this equivalent circuit parameter, what is that you are going to find out? I'm going to find out the rotor ohmic losses. What do you mean by that? See, assume that we are in Hyderabad, and the machine which we need to find out the performance, it is in New Delhi. In New Delhi. If anyone questions you, Are Baba, I want to know the ohmic losses in the rotor winding. Then general procedure is you have to travel to Delhi. Then you have to conduct some suitable experiment, measuring currents in the rotor circuit, something. Then you have to tell the losses in that are this much. But without going to New Delhi, from here only I can tell what is the ohmic losses in that. I'll ask. So can you please tell me what is the rotor winding resistance? 0.1 ohms, sir. Okay. So at what current you need to find out the ohmic losses? The current is 10 amperes, sir. Okay. Then from Hyderabad itself, I can say 10 square into 0.1, it is 10 watts loss is taking place in that winding. So using this resistance parameter R2, I can predetermine, I can pre-estimate the ohmic losses in the rotor circuit. If I know the ohmic losses in the rotor circuit, then this will be helpful to find out the efficiency of the motor without conducting any load test. Then how to know the value of R2, we'll see later. Is it clear? Is it clear? Is it clear? So first, what I'm trying to do means I'm trying to represent the rotor circuit. So let me tell what are the rotor circuit parameters and how these rotor circuit parameters changes with the speed, right? We'll see everything. So after this session, you should be in a position to answer why the starting torque is less. See, in my construction stage, I told you that the starting torque is directly proportional to resistance. As we are using a thicker bars, the area is more, the resistance is less, the starting torque is less. I told you to remember on the basis of some equations. But now we are going to find out what is the true cause, true reason for poor starting torque, very low starting torque. But I told you that once a motor picks up the speeds, once the rotor starts rotating, the torque of that motor will start increasing. We are trying to see now why once the motor starts rotating, the torque will increase. So after this equivalent circuit steps, you should be in a position to answer to this question. So tomorrow, if anyone questions why the starting torque is less, means don't say that our induction torques are told that starting torque is directly proportional to resistance. As we are using a thicker bars, the area is more, the starting torque will be less. Up to till now it is okay. Why? Because you are not seen the performance. But after this, you are not supposed to answer to that. What is that you need to answer? You have to answer this now. Is it clear? Right. All right. So first, rotor circuit parameters. Rotor circuit parameters. Rotor circuit parameters and changes in rotor circuit parameters, from standing to or standstill to. What is the meaning of standstill? When NR is equal to 0 to running conditions. Running conditions with changes in rotor frequency. Changes in rotor frequency or rotor frequencies. Right? Done. So please remember, after this session, you should answer why the starting torque is 6. After this session, how the ohmic losses are accounted in induction machine, by using which parameter we are going to account that. Like that, we are trying to see everything. Please see, first parameter is, as I told you, that when a current is flowing through the rotor winding, then if I observe that if any heat dissipation is coming out, then that heat dissipation is due to the resistive nature of that coil, resistance of that coil. So that resistance, that heating effect is accounted with a lumped parameter R2. So we use R for representing the resistance, suffix 2 for the rotor side. So R2 is accountable for ohmic losses, the heating effect in the conductor. So we are representing with R2. So using this R2, what is that you are going to find out means the ohmic losses in the rotor winding can be calculated, right? Is it clear? All of you confirm me? Confirm me? Right. So before to that, all the following parameters are per phase quantities. All the following rotor quantities or parameters are per phase parameters. First one is R2. R2. So what is this R2? As I told you that rotor winding resistance per phase. Rotor winding resistance per phase. Rotor winding resistance per phase. Per phase. Right? So now this branch has to be represented like a parallel branch, or this branch has to be represented like a series branch in the rotor circuit. So for that, I'll take one example. See, I'm having a simple circuit, 10 volts here, and I'm having a 1 ohm resistance. See, I told you don't text anything as of now, right? Please. See, my voice is clear, all of you remember, right? Right, fine. See, if I take this circuit like this, see, my voice is clear, all of you? Raise the hands. Right, done. See, if I take this circuit like this, 1 or 2 or 1, 1 like this I take it as 2. Then what is the current that flows through this circuit means this 2 ohm resistance means it is always 5 amperes. Always 5 amperes. Even though this resistance is vary from 1 to 2, 2 to 3, 3 to 4, 4 to 5, whatever the changes we are having in the other circuit, or the other rest of the circuit, the current in the 2 ohms, these 2 ohms will always remains 5 amperes only. If it is 5 amperes, the loss in that resistance will be always 25 into 2, it is 50 watts. Is it clear? Is it clear? Raise your hands. Right, done. But if I take this at 2 ohms, if I connect like this, I mean to say it is in series with the source. So if I vary this value from 2 to 3 to 3, 4, 4 to 5, 5 to 6, 6 to 7, 7 to 8 like that, if I vary that resistance, then definitely with that resistance, the current through the 2 ohms will change. And when the current through the 2 ohms will change, definitely the ohmic losses in the 2 ohms will change. Is it clear? So if it is connected in series, the ohmic losses are changing. If it is connected in parallel, the ohmic losses are remaining same. Please confirm me this. Confirm me this. Right. Done. Now the question is, this R2 represent the ohmic losses, and the ohmic losses in the rotor circuit is not fixed. It is not fixed. It depends upon current, and the current flowing in the rotor circuit depends upon the load. We have seen load. When the load on the motor is increased, then the speed decreases. When speed decreases, the relative speed between the field and the rotor conductors will increase, flux cuttings will increase, current will increase, then obviously the ohmic losses should increase. So if the ohmic losses should increase, means this R2 should not be connected across the rotor voltage, but it has to be connected in series with the rotor voltage. Why? Because with the series, the current flowing will change, the ohmic losses will change. So tomorrow, if anyone questions you, whatever that rotor ohmic resistance you have shown, it is a series branch in the circuit or a shunt branch in the circuit, it is a series branch. Why can't be shunt branch? Means if it is a shunt branch, this branch is connected across the rotor voltage, so that current through that rotor resistance will be always fixed, the ohmic losses will remains always constant, but which is against to the practical scenario. So for that, it should be always a series branch. Series branch. Is it clear? Confirm me all of you. Is it clear? Confirm me all of you. Right. Next one is see. If I'm assuming before to that you answered that. If I'm having a voltage source, if this voltage is giving 10 volts, and if I'm having a resistance of say 1 ohm, so how much voltage and current this source is giving? Now this source is giving 10 volts and 10 amperes of current. Then how much voltage amperes it is giving? 100 VA. Then how much power it consumes? 100 watts. 100 watts. Is it clear? So whatever the power the source is giving, the same amount of power the rotor the resistance is taking. So 100 VA, it is taking the same 100 watts of power. Will you agree with me? The same power it is taking from the source. Clear? Raise the hands. Right. Done. Now, if I'm imagining the rotor circuit as a pure resistive circuit, then whatever the power that is coming from stator, the same power has to travel to the rotor. Whatever the power that is coming from stator, the same power has to travel to rotor. But fortunately or unfortunately, as this motor works on induction principle, right? So when the magnetic flux lines are crossing the air gap, some of the flux lines are leaking. Some of the flux lines are leaking. So due to the leakages, the power which is supposed to be transferred to the rotor will be decreasing. In other way, if I'm correct, your teacher might have told you like this. In transformers, I'm not talking in detail. If I'm having a transformer, This is the primary winding. This is the secondary winding. Let me assume. When I connect a load, so this is producing a flux phi 2. If all this flux phi 2 is opposing the main field flux, then 100% of power is transferred. I'm not going to explain more on that. If not, you are going to learn in your transformers. 100% of flux is transferred. 100% of power is transferred from primary to secondary. But very fortunately, if 5% of flux is leaking here, if the 5% of flux is leaking here, only 95% of flux is opposing the main field flux, then what is the amount of power that is being drawn from the primary is only 95% of power is transferred. So who is reducing the amount of power that is coming to the secondary means the leakages. More are the leakages, less will be the power transfer. Less are the leakages, more will be the power transfer. I hope this point is clear. Confirm me all of you. Confirm me all of you. Right. So here in case of rotor, the power is transferred from stator to rotor through these magnetic flux lines. But when the magnetic flux lines are approaching the air gap, they see a change in reluctance, and due to the change in reluctance, there will be a part of leakages. So due to the leakages, the power which is supposed to come from stator to rotor, the entire power is not coming. A part of the power is getting reduced. A part of the power is getting reduced due to leakages. So that is the reason we are not supposed to treat the rotor circuit as a pure resistive circuit. Why? Because if it is a pure resistive circuit, if I imagine, then the power which is coming from stator, the same power has to come to rotor. But unfortunately, due to leakages, a part of the power is going to be reduced. So there has to be one more branch which is accountable for, which is responsible for reduction in power due to leakages. So the other branch is nothing but your leakage reactance. It is accountable for reduction power due to leakages. So what is the other branch we need to represent in the rotor circuit means the leakage reactance, which is accountable for reduction in power due to leakages. Is it clear? Confirm me. Right. So what I'll try to do means I'll try to prepare a table and we'll try to fix one quantity, right? See, so here, see, no textbooks will give all these things. So out of this experience, we have to imagine, oh, which branch we have to represent for effect resistance, which branch we are supposed to represent for a reduction in power due to leakages on the winding inductance, that is leakage reactance. Like that we have to represent. So here parameter. So next one is, I'll just go for some lines. Why? Because here we'll overlap. Parameter, then standstill, then running, then relationship, relationship, right? The next parameter is, as I told you, that leakage reactance. Or rotor leakage reactance. The rotor leakage reactance. So here we are using one notation, X for the leakage reactance, 2 for the rotor side. Already I told you, in addition to 0, we represent for standstill condition. So it is NR is equal to 0. So tomorrow in any exam, in any numerical, in any problem, the rotor leakage reactance at standstill is 0.2. Then you have to take that 0.2 for this X2 naught. So remember, this X2 naught is not taken the patent that in every textbook we are supposed to call it as a standstill rotor leakage reactance. So different others will use different notation. So what is the notation we are using? This much, right? So X2 naught is nothing but, so what is the name I can give it to that X2 naught? X2 naught, can I call it as standstill rotor leakage reactance? Can I call? Please confirm me. Standstill rotor leakage reactance. Can I call? Or can I call like this? Rotor leakage reactance at standstill. Rotor leakage reactance at standstill. So it is accountable for reduction in power due to leakages. So please understand, these are all important terminologies. So omega naught into L2. So omega naught is 2 pi F2. What is the frequency of the rotor circuit at standstill? F. Already I told you. So it is something like this. Then X suffix 2. X suffix 2. What is that X suffix 2 means? X suffix 2 means the rotor leakage reactance during running condition. When there is no zero, then you have to write it as running condition. So this is equal to omega 2 into L2, that is 2 pi F2 into L2. And you know that F2 is equal to SF, then X2 is equal to 2 pi SF into L2, that is S into 2 pi F into L2. And 2 pi F into L2 is nothing but X2 naught. Yes, X2 naught. Then what is the relation we are having between these two? S is X2 is equal to S X2 naught. Now I'm trying to answer to this question. Why the starting torque is very poor? Then we can see at starting the rotor frequency is how much? 50 hertz. As the rotor frequency is 50 hertz, the leakage reactance or the rotor circuit will be high inductive in nature. High inductive in nature. As the rotor circuit is high inductive in nature, then what is the power factor of the rotor circuit? Very, very poor. Why? Because when compared to resistive part, the inductive part is very high. The rotor circuit is highly inductive in nature. The power factor will be less. When the power factor is less, the active power drawn by the rotor circuit will be less. When the active power drawn by the rotor circuit is less, the torque which depends on that active power is also less. So tomorrow if anyone questions you, are why at starting the torque is very less? You can see when compared to the resistance R2, the leakage reactance X2 naught is very high. Why X2 naught is very high? Frequency is 50 hertz. As the leakage reactance is very high, the value is large compared to the resistance. The rotor circuit is high inductive nature. When the rotor circuit is high inductive nature, the rotor power factor will be very, very less. When the rotor power factor is very, very less, the active power drawn VI cos phi. Because of poor power factor, the active power drawn will be less. The torque which depends on that will be less. So that is the reason the starting torque of an induction motor is less. But once the motor starts picking up, once the rotor speed starts increasing, the torque will increase. By once the motor starts rotating, the slip value will decrease. At starting, slip is equal to 1. But once the motor picks up the speed, the slip decreases. When slip decreases, what happened to that? X decreases. So when X decreases, the inductive nature of the rotor circuit will start decreasing. When it starts decreasing, the power factor will improve, the active power drawn will increase, the torque which depends on that will also increases, and hence the torque value will increase. Is it clear? Confirm me. Is it clear? Confirm me. Right. So tomorrow if anyone questions you, right? So this is the reason, this is the answer which you are supposed to give. Even with respect to that magnetic poles also we can say. So when the rotor at starting, the distance between the stator field and the rotor field is too long. Why you will see? As poles are very far away, then attractive and repulsive forces are weak. As attractive and repulsive forces are weak, the torque will be very, very less. But once the motor starts rotating, the distance between the stator field and the rotor field will come closer. When the poles are coming closer, those attractive and repulsive forces will be strong. Something like distance matter more. Far distance, no affection. Close, very high affection. The same thing. If the poles are far away, the attractive forces are less, torque is less. If the poles are very close, the attraction will be more, the torque will be more. Why? We'll see. But as of now, you can answer what is it? At starting, what is the frequency of the rotor circuit? 50 hertz. The rotor circuit is high inductive in nature. When the rotor circuit is high inductive in nature, the power factors will be very poor. The active power drawn will be less. The torque which depends on that will be less. But once the motor starts picking up, once the rotor starts rotating, the frequency will start decreasing. The reactance will start decreasing. The power factor will start increasing. The active power drawn from the rotor will start increasing. The torque which depends on that will also increase. So this is the relation. Please confirm me once, all of you. Right. Now the question comes, even this is a series branch or a shunt branch. It is also a series branch. Why? Because leakages depends upon current. More current, more leakages, less current, less leakages. Again, current is a series parameter, a shunt parameter. It is a series parameter. So in the equivalent circuit, you have to show this leakage reactance also as a series branch, series parameter. Done. The next one is the rotor EMF. The rotor EMF. Or in other way, the EMF induced in the rotor winding, right? So I'll write this here, E2 naught. So what is the name I can give it to that E2 naught? The EMF induced in the rotor winding per phase at standstill. So it is 4.44 F phi R N2 kW2. Then what is the EMF that is induced in the rotor winding during running condition? 4.44 F2. Why I have taken directly F here? There is not here. At naught, the frequency is F. F2 phi R N2 kW2. And you know that F2 is equal to SF, and I can write E2 is equal to SE2 naught. Then here, what is the relation we are having between these two quantities at standstill and running? E2 is equal to SE2 naught. Yes, E2 naught, right? I hope this is clear. That is the reason at starting the rotor voltage is maximum. Why? Because the relative speed is ns minus rotor speed is 0. Ns minus 0, the relative speed is maximum, EMF is maximum. But once the motor starts rotating, the relative speed will start decreasing, the rotor voltages will start decreasing. That's the relation. E2 is equal to S into E2 naught. Please confirm me. Raise the hands. Right, done. The next parameter is the impedance. Impedance. Rotor leakage impedance. Rotor leakage impedance. Rotor leakage impedance. At standstill, I write Z2 naught in rectangular form R2 plus J X2 naught. Then what is the magnitude of this? Square root of R2 square plus X2 naught square. Then during running condition, it is Z2, which is R2 plus J X2, which is R2 plus J S X2 naught, which is square root of R2 square plus S X2 naught whole square. There is no relation between these two. Why? Because the resistance parameter is there in the impedance parameter, right? Done. The next one is the rotor current. The next parameter is the rotor current. So what is the formula for rotor current? So current is equal to the voltage by impedance. So it is E2 naught by impedance is how much? Square root of R2 square plus X2 naught square. So here I2 is equal to E2 by Z2. So that is equal to S E2 naught by square root of R2 square plus S X2 naught whole square. Then what is the relation we are having between these two? No relation. Then the next parameter is rotor power factor. So all I am writing basing the rotor circuit is a R with variable X, right? RL circuit. Next one is rotor power factor. Rotor power factor. What is the formula for rotor power factor? Cos theta 2 naught at starting is equal to R2 by square root of R2 square plus x2 naught square, and during running, see, if I want to solve numericals, I can solve any numerical giving R2, X2 naught, yes. So that I don't think it is a gate question or engineering service question. We'll see some standard questions later. See, X2 naught square. Then what is the relation? No relation. So finally, I'll draw the rotor equivalent circuit. Rotor equivalent circuit. This is what we required finally. A rotor equivalent circuit. It is called as modeling. So what is that rotor? So you know what is the meaning of modeling? Modeling. I think nowadays the people are projecting third wave, fourth wave. They are drawing some models. So some graphs they are drawing. So in future it will be like this. But no one has tested what will be the cases in the future. So they have not tested any data. But basing on the existing result, they are modeling. So here also, so using this rotor equivalent circuit, we can find out the performance of that machine. It is modeled like this. The circuit is modeled like this. So what is that? I'm having a resistance. I'm having a inductance which are connected in series. And this is R2. This is JX2 naught. And this is E2 naught. And this is I2 naught. So this is the equivalent circuit of the rotor at standstill. Then during running condition, what is the equivalent circuit we have? It is R2, JX2, this is E2, this is JSX2 naught, and this is I2. So this is the equivalent circuit. There is no relation. I hope you understood all of you. Please confirm me all of you. Raise the hands. Right. So finally, can you please tell me with the rotor frequencies or with rotor speed, which branch only is changing in this case? Only the rotor resistance is changing. The rotor resistance is fixed. All other parameters are changing with the rotor frequency, and this rotor frequency changes with speed. When the speed is zero, rotor frequency is supply frequency, and when the speed increases, the rotor frequency decreases, the parameter values are decreases. But only one parameter value will be same. Which parameter? Resistance. So can I say except the rotor winding resistance, all the parameters of the rotor side depends upon the frequencies, and this rotor frequency depends upon the rotor speed, right? Whenever the speed is changing due to the load variation, the frequency changes, and accordingly the rotor parameters also changes, and hence the power drawn and other parameters will also change. Why? Because it is true, when there is no load, then the power drawn should be less. Accordingly the parameters will be like this. Whenever you are varying the load, increasing the load, the parameter should change so that it draws more current, more power and fed to that load, right? Is it clear? Confirm me all of you. Is it clear? Confirm me all of you. So can I write a note here? Except, note, except, note, except the rotor winding resistance, a rotor winding resistance, winding resistance, a resistance, all the parameters of all the parameters of the rotor side depends on the rotor frequency, a rotor frequency, and this rotor frequency depends on a rotor speed, a rotor speed. Please confirm me all of you. Raise the hands. Raise the hands, all of you. Right. Next. So now we are successful in representing the rotor circuit electrically. It is not complete, partially we have represented. So as of now, if anyone questions you, Are Baba, can you please tell me the reason why the starting torque is less? Yes, I can tell. Why the starting torque is less? At starting, the rotor circuit is high inductive in nature. The rotor power factor is very poor. The active power drawn by the rotor is less, and the torque, which depends on that, will be less. But once the motor starts rotating, the inductive nature start decreasing, the resistive nature will start increasing, the power factor will increase, the active power drawn will increase, and the torque will increase. Is it clear? Confirm me. Is it clear? Confirm me. So in other way also I can explain. In other way I can explain. In other way, with the help of phasors, I can explain. Just this is only to make you understand, right? Why? Because if the attractive and repulsive forces between stator poles and rotor poles is strong, then even if I'm trying to apply more load, it can pull. If this attractive forces is weak, then it is something like it cannot. See, something like this. I'm holding the hand of another person, right? So tightly. If this force is strong, if this bonding is strong, even if someone is pulling from other side, so unless and until this force is strong, he cannot take that person away. Is it clear? Confirm? Confirm? Raise the hands. But very unfortunately, that fellow is holding my fingertip and he's far away. And if other person is trying to pull that side and the bonding is very weak, then that person will take that person away. So that person will be left there. I can run this side, right? Is it clear? Confirm me. Confirm me, all of you. Right. Now let me explain why at starting the torque will be less. The torque will be less, right? So I'll recall my torque concept. What is that? In any motor, the torque will be due to the attractive and repulsive forces, right? If those attractive and repulsive forces are strong, then obviously the torque will be maximum. Now, if you just recall the phasor diagram which we have just drawn, this is the resultant field. This is the resultant field. Let me call this one as a north pole, just for imagination purpose, north pole. As this field is rotating, this is inducing an EMF in the rotor circuit, which lags by an angle 90 degrees. At starting, which one is having, rotor circuit is having high inductive nature. As the rotor circuit is having high inductive nature, so that rotor current will lag almost by an angle 90 degrees. Because of this, there is one rotor field. Let me assume that this is a south pole. Then because of the attraction, as this pole is moving, because of this attraction between the stator poles and the rotor pole, the rotor will rotate. But very unfortunately, the angle, the spatial angle between these two poles is 180 degrees. Those attractive forces are very weak. That's the reason the turning effect is very weak. Is it clear? Confirm me. Is it clear? Confirm me. Right. But once a motor starts rotating, what happened to the inductive nature? Decreases. When the inductive nature decreases, what happened to the resistive nature? Increases. And this current will be trying to be in phase with this. When it is coming to be in phase, then you can see the south pole is going closer to that north pole. Not exactly close, it is going very closer to that north pole. Then when compared to starting, that pole is coming closer. When that pole is coming closer, what happens to the attractive forces? Increases. What happens to the torque? Will increase. Then the motor torque will increase. Even if you load the motor, because of the strong torque, the motor can drive the load also. But at starting, because of the far away distance, if you are trying to load the motor, because of these weak forces, the motor cannot rotate. So the rotor will remain stationary. Is it clear? Confirm me. Confirm me. Right. So I have explained maximum thing with respect to starting torque. See, three ways you can explain. Three ways. Why the starting torque is very, very less. In practice and in general in squirrel gauge motor, I'll tell. In case of squirrel gauge rotor, the rotor circuit is highly inductive in nature. That is the reason the active power drawn will be less, the torque will be less. In other way, with the help of this phasor diagram, at starting, as the rotor currents are almost lagging by 90 degrees, those rotor poles are away from the stator poles, almost 180 degrees. As they are away from the stator pole, those attractive and repulsive forces are very, very weak. That's the reason the motor cannot be rotated with high loads. But during running condition, as that inductive nature is decreasing, so the poles are coming closer to that stator pole. The attractive forces will increase, the torque will increase. But in case of your slip ring induction motor, what is that we are doing? We are adding some resistance. When you are adding some resistance, you are forcing these rotor currents to become resistive. Then that current will be trying to be closer to E2. It is closer to 90 degrees. The attractive and repulsive forces will be maximum and the torques will be maximum. Is this point clear? Confirm me, all of you. Right. So till yesterday, we discussed why the starting torque is less basing on the resistance parameter. Starting torque is directly proportional to resistance. As resistance is very less, the starting torque is very less. But truly speaking, the concept is the rotor circuit is high inductive in nature. The active power drawn will be less. The torque which depends on this will be less. Or the rotor poles will be far away from the stator poles, almost 180 degrees. The attractive and repulsive forces are weak, and hence the torque will be weak. But once the motor picks up the speed, the current will becomes resistive current. That poles will be coming closer to the stator poles. Those attractive and repulsive forces will increase. The torque will also increases. Right? This is something about the starting torque concept. Done. So I think by this time you should imagine, oh, what is that? Oh, induction motor starting torque is very, very poor. Why? The rotor poles are away from the stator poles. Those attractive forces are very weak, and hence the motor cannot be loaded heavily. But if I try to make the rotor circuit high resistive, then we are making the rotor poles to come closer to that stator poles around 90 degrees. Then those attractive and repulsive forces will increase, the torque can be increased. So if I want to make the rotor circuit highly resistive, so during starting I have to add some resistance. So that is possible in case of your resistance. Sorry, in case of slip ring rotors. I hope this is clear. Right? Done. The next concept is, finally, you raise the hands once. With this, we'll proceed to the next concept. Right, done. The next concept is power flow. Power flow in induction motor. Power flow in induction motor. Induction motor. Induction motor. So this is very, very important concept, right? In every engineering service, definitely there will be a question, one or two questions from this power flow. And even in GATE also, chances are maximum that there may be a question from this power flow. So you should think that whenever there is some flow, definitely there will be some loss, right? I'll give a general example. After that, I'll come back to this power flow concept, right? See, if I take a multi-purpose dam, some dam, what is the main purpose of the dam? Means to store the water during this rainy season, so that water will be collected in that catchment area, right, where we have heavy rainfalls, where that plateau, where that heights are less, we constructed dams, so water will be collected. And during rainy season, that water is being collected, and during non-rainy season, when we need water for this agriculture purpose or for this generation purpose, that water is being used. And for agriculture purpose, that water is supplied through river. So generally, if you look a river, it is a open channel, right? Through that the water will be flowing. Say, let me just talk on the basis of liters, some 10 liters, 5 liters, something like. Say, I don't know gallons or cubic gallons, that I don't want to talk. Some general terminology I'll use. Say I'm supplying some 1,000 liters of water. It is very less. Just I'm talking 1,000 liters of water from a dam. And I want to transfer that 1,000 liters of water to some 100 kilometers distance. So is it like the same 1,000 liters of water going to that 100 kilometers? No. Why? Because as that water is flowing in a dry land first, a part of the water is going to be absorbed by the dry land. And as that water is flowing in the open sun, a part of the water is going to be evaporated. And in between, somebody may take some water. So all these are the losses. So finally, on the other side, so I may have some 100 or 200 water received at 100 kilometers distance. That means if I talk with respect to this water flow, the losses are due to absorption, the losses are due to evaporation, the losses are due to water theft. Somebody may take that water, so because of that we may have the water loss, right? So finally, see, I don't know this number, so he's continuously raising the hand, only 1%. See Baba, if I'm correct from my side, I don't have any technical issues. So please try to rectify from your side. Why? Because you are the only person who is raising the hand. So other persons are not raising the hands, right? Please try to rectify if any technical issues are there from your side. So please confirm me once if my network and other things are clear. All of you raise the hands. Yeah. So you are the only one. You try to rectify from your side. I don't know. He is Gopal Reddy, Venu Gopal Reddy. Please, Venu Gopal Reddy, try to rectify if any problem is there from your side. Right? Please, Venu Gopal Reddy. Right. Right. Fine. Power flow. Right. So I have taken a general example. Whenever a water is flowing, we have loss in that water content. Right. Done. Similarly, here also, in case of an induction motor, we give some electrical power, and that power has to travel through the stator, and Monica, please see, and that water has to that the power has to travel through the stator core, and it has to cross the air gap, and it has to go to the rotor. Then the rotor has to convert that electrical power to mechanical, and that mechanical power has to travel via the shaft, and that mechanical power has to be made available across the shaft for the load, and that load can collect that mechanical power from the shaft. I think this is the flow. Once again I repeat, we are giving some electrical power to 1 minute, right? We are giving some electrical power to stator. Then what this stator has to do means it has to see that the power is flowing through the stator, crossing the air gap, going to the rotor. Then the rotor has to take that electrical power, convert that electrical power into mechanical. The rotor has to rotate, and that mechanical power has to flow through the shaft, and that power has to be available to the load. And the load can take that mechanical power and it can rotate. Something like this, bad blades can rotate, right? I hope this is the power flow concept, right? In general, please tell me if it is clear. But very unfortunately, when this power is flowing from stator through stator circuit to rotor, there is some loss in the stator circuit. Similarly, when the power is coming to the rotor, before it is converted into mechanical power, there is some loss in the rotor circuit. After that, electrical power is converted into mechanical. When it is passing through the shaft, it is available at the load. There is some loss in that shaft transfer, or that when the power is traveling via the shaft. So we are going to see when this power is flowing through the circuit, so in which part of the machine the losses will be taking and why the losses will be taking. And we are going to talk about this power flow concept. Is it clear? Confirm me all of you. Is it clear? Confirm me all of you. All right. So here what I'll try to do means I'll take an induction motor. So this concept of explaining in a friendly conversation way. Just something like I'm speaking to that induction machine, friendly in conversation I'm trying to explain. A friendly conversation I'm trying to explain, right? Please see. So what is that friendly conversation? Please see. So I'm taking a 3-phase induction motor. And this 3-phase induction motor is my thickest friend. Then you may have a doubt. Sir, this fellow is a non-living thing and you are a living thing. So why? Because you are talking and just doing all physical activities. You are a living thing. Then how come a non-living thing can be a friend to you, sir? Right? Why? Because I'm talking or I'm taking this subject induction machine, or particularly this induction or machines for the past 12 years, more than a decade. So that is the reason this fellow become the thickest friend for me, right? And one more thing is, if I'm correct, so there are very rare cases that non-living things can hurt compared to the living things. So living things will definitely hurt, but non-living things cannot hurt. So for that reason, most of the time it is better to have friendship with non-living things, right? So knowingly or unknowingly, one more thickest friend in your life, the non-living thing is your mobile, right? So like this fellow is my thickest friend, right? So I'm talking to my thickest friend, my dear friend, how are you? So he is responding to me. Who is responding? Induction motor. I am very super fine, super duper fine. I am, right? SOOPER, super DOOPER, duper, super duper fine. Of course, the spelling is wrong, right? So he is responding to me, super duper. Now I'm speaking to this induction motor, and I'm talking to that induction motor. My dear friend, I give some 40 kilowatts of electrical power to you. How much power I'm giving? 40 kilowatts of electrical power. So I'm using this notation: P for active power, S for stator side, I for input. I'm giving 40 kilowatts of electrical power to you. Please see that you take this 40 kilowatts of power and convert this 40 kilowatts of electrical power into mechanical, and I need that mechanical power to rotate something. So I'm speaking to the stator of an induction motor. Then EP means electrical power. Again, you will type what is EPs are, electrical power, right? Then that stator is responding to me, my dear friend, I'm very sorry. I cannot convert your 40 kilowatts of electrical power into mechanical. The reason is I'm a stationary part. I cannot rotate. But if you can trust me, if you can believe me, right? So I'll see that this 40 kilowatts of power is transferred to the rotor via my circuit. And I'll request my sister concerned rotor to please convert this 40 kilowatts of power into mechanical power. And from the rotor, you can collect this mechanical power. If you can trust me, you can use this 40 kilowatts. And I take this 40 kilowatts and I'll see that this 40 kilowatts travels along my stator core, reaches the rotor, and I'll ask the rotor to convert this power into mechanical. If you are trusting me, you can give this power to me, right? Then I'll answer to my stator, P Manohar. Please try to see. See, I told you, if you are raising the hands means only because of some voice breaking or internet problem. If one or two are raising means it is your side. If a bulk is raising means it is from my side, but I can see only one or two. So you check your network connection, not me, right? Please. Right. So how much power I'm giving to the stator? Now 40 kilowatts, but the stator is responding to me. So if you can trust me, so you can give this 40 kilowatts, and I can see that this 40 kilowatts is traveling to the rotor, and I'll ask the rotor to convert this power into mechanical, right? Then I'll respond to my stator. Arey kya baat bole aapne? So you are my thickest friend. I trust you blindly. You can take this 40 kilowatts of power, and you can see that this 40 kilowatts of power is going to the rotor, and you tell the rotor to convert this 40 kilowatts, and I'll collect that mechanical power from the rotor. Is it clear? Confirm me. Is it clear? Confirm me. Raise the hands. But keep this mind, never ever trust anyone. Sometimes your shadow also. Never ever trust anyone. Why? Because sometimes the salt and sugar looks like same if it looks from far, but they're totally different. Don't ever trust anyone, right? But anyhow, I'm trusting the stator. Why? Because as he is my thickest friend, and I'm giving 40 kilowatts of power to the stator, and I'm waiting that the stator will make this power to flow to the rotor, and from that rotor I can collect this mechanical power. Now the stator took 40 kilowatts of power from me, 40 kilowatts of power from me, right? Then who is taking this power means the stator windings. Just it is only the imagination, right? Don't think clearly. Imagination. Who is taking this power? Stator windings. So in the form of current. So form of current means moving charges, electrons. So finally, who is taking this current means, and the power means the electrons which are present in the stator winding. So it looks like this 40 kilowatts of power is taken by those stator winding electrons. So their role is to carry this power and convey this power to that rotor circuit. But very unfortunately, the electrons which are carrying this power, they are excited. As they are excited, they will collide with each other. They will rupture with each other. They will fight with each other. They will hit with each other. So for all that, they need power. So from where they take that power means from the power what they are carrying to give it to the rotor. So they take that power for fighting, for collision, for rupturing, and all these things. So the stator circuit is watching. You're a stupid fellow. Your work is only to carry that power and give it to the rotor, and unnecessarily you're fighting with each other. You're wasting some power, and you're spoiling my name in front of my friend, wasting some power, taking some power, and those electrons will respond to me. You don't talk much. Why you are crying on us? We are taking a part of the power. We are doing some work, and we are taking a part of the power. Why you are crying on us, right? Let us enjoy. Let me take some power. Let me fight with each other. Okay, if that is the case, go ahead. Then the first laws, while this power is traveling, when this power is flowing, will be in the stator winding, and that is due to that winding resistance. So the name given to that loss, we call it as the loss due to winding resistance. The loss due to that ohmic resistance, that loss we call it as ohmic loss. Or to be more general way to tell, it is called as a copper loss. Why? Because what is the material we are using? Copper. So as the loss is taking place in the copper, we are naming it as a copper loss. But truly speaking, it is the loss due to resistance or the ohmic loss. I hope this point is clear. Confirm. Confirm. So where is the first loss taking? Where is the first law? 1 second. I'll have a water and come back. 1 second. Even I have to put charging also. I'll put and come. Right. Please confirm me, all of you. Can you see me? Yes. So where is the first loss taking place in induction machine means in the windings. Which winding? Stator windings, right? So let us consider it is P, S, C, L. Our notation is stator copper losses. Stator copper losses. Stator copper loss. Right? Then the stator feels that okay, this power is going to rotor. Okay, so as those electrons are doing some work, they are taking a part of the power and they are enjoying. Let it be what is there. Okay, they are taking. Meanwhile, the core. So what is that core? If you remember the stator construction, so we'll be having windings and these windings are placed in the slots and these slots are made in the core, right? Now this core will speak, hello, my dear stator. What is that you are just seeing the windings? Not only the electrons which are fighting in the conductors, but the electrons which are present in the core, which are present in the stator core are also fighting. How come? I'm not giving any excitation to the core. Then how come the electrons which are present in the core will be fighting? Means it is true that the core is not excited, just like your windings are excited. As we are passing current through the winding, we are not passing any current through the core, but still the electrons which are present in the core are fighting. How come? Can you please tell? Yes. So that is due to induced current. Why? If you remember the stator construction, so this is the stator construction. This is the core. Just I'm drawing a part, right? So these are the magnetic poles. So these are the magnetic flux lines. So if I consider a section of the core like this, any section of the core like this is the section of the core. If any section of the core, if I consider section of the core, if I consider a part, a long part, if I consider, as of now, there are no flux lines passing to that section of the core. But as these poles are rotating, in the next moment, this pole will come here, and through that you can see the magnetic flux lines are passing. So with respect to that section of the core, the flux lines are changing, or the number of flux lines passed through that core are changing. So due to these changes, what is induced in that? An EMF will be induced, right? Is this point clear? Confirm me. Is this point clear? Confirm me. What happened? Okay, search. 1 second. Right. So an EMF will be induced inside the core. And if that EMF finds a closed path, what circulate? Current. So that current will heat up the core. That loss we call it as a eddy current loss. Now the core will respond to that C. It is true that you are not passing any current through the core, but because of the currents which are flowing through the winding, poles are formed in the core, and the nature of these poles are rotating. While they are rotating, they are cutting the core inside. As they are cutting the core inside, an EMF is induced inside the core, and as that EMF finds a closed path, the currents are circulating. Nothing but the electrons which are in the core are in motion charges, and they are fighting with each other. They are colliding with each other. For that, they need some power. So from where they that fighting electrons will get the power means from the power which that electrons are carrying, or the power which is flowing through the stator circuit. So where is the second loss will take place means the second loss is taking in the stator core due to that core resistance, or due to that electrons which are present in the core. Why? Because that is also a magnetic material, also a good conductor of electricity. Because of that there is heating. That loss we call it as ohmic loss. So where is the second loss taking place means the second loss is taking place in the stator core due to that induced current and due to that core resistance. But whereas the first loss will be due to supply current and winding resistance, the second will be due to that core resistance and due to that induced current. How the currents are induced? As these poles are rotating, they are cutting the flux lines. Those flux lines are cutting the core, and EMF is induced, and that EMF finds a closed path that will circulate a current. So due to that current, there is some loss. That loss we call it as eddy current loss. In other way, that is also called as the loss due to core resistance. So it is also called as ohmic losses in the core. So what is the other name we can give it to that eddy current losses? Means the loss due to core resistance or the loss due to induced current. In cut short, it is the ohmic loss in the core. Is it clear? Confirm me, all of you. Right. So the second loss will be in the core, in the core, and it is due to eddy currents. Eddy currents. Eddy currents. Right. So I'll write it as the core losses in the iron. So stator iron losses. Right. We are using iron. Eddy current losses. Not only this eddy current losses, we have one more losses. What is that one more losses? Hysteresis losses. So I think your transformer teacher might have explained. If not, you are going to learn in transformer. What are hysteresis losses? What are those hysteresis losses means? You may be knowing. Just I'm highlighting. What is that? If I take any magnetic material, inside this magnetic material will be having small dipoles, small magnets, dipoles, small dipoles will be there. And these dipoles will be randomly oriented. But when I'm trying to pass a AC through that, you can see during 0 to 90, the magnitude of this current is increasing. Then when the magnitude of the current is increasing, all the dipoles which are there will try to align like this, will try to align. So when the current is reaching to its peak value, then it is true that all the dipoles will get aligned like this. They are perfectly aligned. But after peak value, when the magnitude of current is decreasing, then the dipoles which are been aligned should come back to their original position. What is the original position means? Random position. This position they need to come back. But very unfortunately, it is not like all dipoles will come back to their original position. Due to that magnetic inertia, some dipoles will be still in aligned position only. Some dipoles will be still in aligned position only, even the current is zero. So because of that, there is some flux retain. There is some flux retain in the core. That property we call it as retentivity, right? In cut short, that flux we call it as a residual flux. So this flux is mainly responsible to build up the voltages, particularly in case of self-excited machines that you learn in that machines concept, that is other machines. So I hope this point is clear. Confirm me, all of you. So even though the current is zero, some of the dipoles will remain in aligned position because of that magnetic inertia. So they will retain some magnetic flux. They retain some magnetism that we call it as retentivity, in short, the residual flux. Now, after the zero, when the current is going back, or it is traveling the negative cycle, all the dipole should reorient in opposite direction. Reoriented in opposite direction. But very unfortunately, the dipoles which are aligned like this because of the previous excitation, so they need some power to come back to that random position. Only when the dipoles are in random position, then they have the flexibility to align like this or like this. But you can see here all these dipoles are randomly oriented, so they don't have any issue to realign in opposite direction. But these dipoles which are still in aligned position, if they want to come back to that, or if they want to realign in opposite direction, so first they should be brought to random motion. They need to be brought to random position. For that, they need some power. They will take that power, and once they are random, then they don't take any power. They can realign in opposite direction. So the loss, that is the power that is required to de-align the aligned dipoles to random position so that they can be realigned in opposite direction, that loss we call it as hysteresis loss in shortcut analysis, shortcut explanation. Is this point clear? Confirm me. Right. Once again, so initially, what is the position of these dipoles? They are randomly oriented. They are freeboard, right? Freeboard. They are randomly oriented. But when I place a coil on that, when I try to increase the magnitude of current, I'm not increasing manually. So because of the virtue of the current, nature of the current, as it is an AC, the current magnitude will be increasing. When the current magnitude is increasing, the number of dipoles which are trying to align will start increasing. So when the current is reaching to the peak value, let us assume that all the dipoles are being aligned. But after that, when the current start falling from peak value, the current magnitude is decreasing. The dipoles which are been aligned should come back to their original status, dipole, randomly movement. So they have to come back. So some of the dipoles are coming back. So when the current is zero here, when the current is zero here, all the dipoles should come back to their random position. But few dipoles will still remain in aligned position because of this magnetic inertia. But after that zero, the current will take the opposite direction. Then this dipole should realign in opposite direction. But only the free dipoles which are randomly oriented has a possibility to realign in opposite direction. But the dipoles which are previously aligned, if they want to realign in opposite direction, so first they should brought to random position. So for that they need some power. So from there, that loss we call it as hysteresis loss. So that is the reason, if the nature of the BH curve is linear, that means with the increase in current, if the flux is increasing linearly, that means with the increase in current, the dipoles are increasing linearly. When you are decreasing the current, all the dipoles are coming to the random position. When current is zero, the dipoles are random. The hysteresis losses in that case will be zero, right? I hope this point is clear. All of you confirm me. So I hope you understood hysteresis losses. Now here what is happening is, see, now let me explain hysteresis. So here in this case, when this is a north pole, let us assume that the dipoles are oriented downwards. But after half cycle, which pole will come here? South. Why? Because what is the nature of that poles in the stator core? They are rotating. Then what should be the nature of these dipoles? They should realign in opposite direction. But when there is a north pole, some of the dipoles will be still in aligned position because of the magnetic inertia. When the south pole is coming to that position, so these dipoles cannot come back to their original position, random position. So there should be some power that is required to make that aligned dipole to random so that they can realign in opposite direction. That loss we call it as a hysteresis loss. Is it clear? Confirm me, all of you. Right. Now can I say the stator is in opinion that whatever the power that is given to the stator will be collected by this stator current, and that power is fed to that rotor. But very unfortunately, these stupid fellows which are present, those electrons which are present in the stator windings, they are excited and they're fighting, they are taking some power. It is a foolish thing. But anyhow, as they are doing some power work, let them fight. So part of the power is wasted in the stator winding. But very unfortunately, those who are not doing any work, but they need some power. Why? So as the poles are rotating, the flux lines are rotating. When the flux lines are rotating, they are cutting the flux lines, the stator core, and EMF is induced. Because of that EMF, there is some loss that we call it as ohmic losses in the core or eddy current. Then the dipoles which are present in the stator cores will say, hello, my dear stator, you are very much partial. You are looking only into the electrons. They are fighting and they are wasting some power. What about our case, the dipoles? We are changing our orientation for every half cycle. Then we need some power to come back to the random position. Please give some power. Then only we can change our orientation. Okay, take. So finally the stator will compromise. So for what you need power? So those electrons says for us, the core electron says for us, the dipoles will say for us. So instead of using the terminology for us, there is a loss in the stator winding, there is a loss in the stator core due to that ohmic resistance, and there is a loss due to the reversal of the dipoles. And we are giving a technical names, the stator winding ohmic losses, the stator core eddy current losses, the stator core hysteresis losses. Now finally stator says for all this how much you are need 2 kilowatts. Let us take 2 kilowatts. So how much power is wasted here? 2 kilowatts of power is wasted before it is reaching to the rotor circuit. Is it clear? Confirm me. Is it clear? Confirm me. So can I write like this? Can I write like stator losses means, please see, stator losses means I'm representing like P, S, L. So the stator losses are stator winding resistance loss. So that we call it as copper loss also. Why? Because what is the material you are using for that windings? Copper loss, right? So I'm representing like stator copper losses. The other one is core losses. Core losses. In these core losses, what are we are having? Eddy current losses. Eddy current losses. Why? What are these eddy current losses? These eddy current losses are due to the induced EMF. This induced EMF is due to that flux cutting the core. Why the flux is cutting means the poles are rotating. So eddy current losses. The other one is hysteresis losses. What are these hysteresis losses means? The poles are rotating, then the dipoles which are inside the core, they should change their orientation for every half cycle. For that, they need some power. This is called hysteresis losses. So I represent these losses as stator iron losses. Why? Because they are taking in iron. So stator losses means, can I write stator losses means sum of stator core plus stator iron losses. Iron losses. So in this case, how much is required? Let us take 2 kilowatts is required. Is it clear? Confirm me all of you. Is it clear? Confirm me all of you. Right. So now how much power is going to the rotor now, or how much power is crossing the air gap now? 38 kilowatts. But my intention is to give how much power to the rotor now? 40 kilowatts. But very unfortunately, a 2 kilowatts of electrical power is wasted in the stator while that power is crossing the stator circuit. So while the power is crossing the stator, a 2 kilowatts of power is wasted. So here, a 2 kilowatts of power is wasted. So a 2 kilowatts of power is wasted. A 2 kilowatts of power is wasted. Stator losses is equal to 2 kilowatts. 2 kilowatts. Now how much power is going to the rotor now? So it is 38 kilowatts of power is going to the rotor. So how much power is going to the rotor now? So it is the stator output power, nothing but the rotor input power, nothing but the air gap power. All are same. So how much power is going to the rotor means? So can I use this formula? Stator output. So PSO means stator output power. RI, rotor input power. PAG means air gap power. All are same. All are same. So this is equal to stator input minus stator losses. So it is 40 minus 2. So it is 38 kilowatts. So this amount of power is going to the rotor now. But my intention is to transfer how much power to the rotor now? 40 kilowatts. But because of the losses, a 2 kilowatts is wasted in the stator circuit. Is it clear? Confirm me all of you. Is it clear? Confirm me all of you. Right. Now the stator is instructing the rotor. My dear sister concerned rotor, I have given a word. I have promised my friend that I'll be converting that 40 kilowatts of power to mechanical. But very unfortunately, stupid stator winding, stupid stator core, combinedly they are taking 2 kilowatts from this 40 kilowatts and they are giving 38. At least you being a sister concerned of mine, convert this 38 kilowatts of power into mechanical. Then the rotor will say, see, so this power has to flow through the windings, the rotor windings, and those stupid electrons which are present in the rotor windings will also fight. they will take some power. So we cannot avoid. So that is inevitable, right? I cannot avoid that. So definitely some power will be taken by those electrons which are present in that rotor windings. Okay, leave it. But don't worry, there will not be any power in the rotor core. Why there will not be any power in the rotor core means, as we have seen, the frequencies of the rotor currents are very, very less. Then the number of times the poles are reversing will be very less. Then as the rotor speed is very closer to the synchronous speed, the flux cutting the core, the flux cutting the windings will be less. So eddy currents will be less, hysteresis losses will be less. So which losses we can ignore in the rotor circuit means the core losses can be ignored. Why? Because the frequencies are very less, it can be ignored. So the losses in the rotor means it is only due to the fightings in the winding. It is only due to the winding resistance, that is rotor winding resistance. Is it clear? Confirm me. Is it clear? Confirm me. So here the losses will be only in windings. So let us call it as rotor losses, and that is due to that winding resistance. So how much is wasted there? 1 kilowatt, right? Then how much is the power that is converted into mechanical power now means? First let us see. So here the remaining power goes to rotor. Sorry, it is converted into mechanical power. That power I call it as rotor output power, which is the mechanical form, or internal mechanical power. Why? Because who is rotating inside rotor core? So that is the internal mechanical power, IM, or it is called as a gross mechanical power. Gross mechanical power, right? So what is the names? So rotor output power, right? PIM, internal mechanical power, mechanical power. PGMD, gross mechanical power developed. Mechanical power developed. Power developed. So this is equal to a rotor input minus rotor losses. So what is the rotor input here? 38. Rotor losses are 1. It is 37 kilowatts. So this is the mechanical power or mechanical form, right? Our intention is to convert how much electrical equivalent into mechanical power. 40 kilowatts of electrical equivalent we need to convert into mechanical power. But very, very unfortunate thing is, out of that 40, only we are able to convert 37 kilowatt of electrical power into its equivalent mechanical power. Why? Because out of that 40, 2 kilowatts is wasted in the stator circuit, 1 kilowatt is wasted in the rotor circuit. Total 3 kilowatts is wasted in the stator and the rotor circuit, right? So how much electrical equivalent is converted into mechanical? Only 37 kilowatts of electrical equivalent is converted into mechanical. Is this point clear? Confirm. Right. Done. So now 37 kilowatts is converted into mechanical power. You can see here. You can see here. See, after this I'll give break. So this is electrical power, and only this is mechanical power. But who is rotating inside means rotor core. Rotor core. But I cannot directly place the load on the rotor core. See, if I'm having blades, I cannot go inside the core and place the blades. No. So that mechanical power has to be brought out. So who is bringing that mechanical power out? The shaft. But very unfortunately, that shaft, when it is coming out, it is passing through the ball bearings. And in case of slip ring, induction motor, it is passing through the slip rings. And when it is coming, due to the friction at ball bearings and due to the friction at the slip rings, the speed decreases. When the speed decreases, P net is equal to torque into omega. When the speed decreases, the output mechanical power is also decreasing. That means whatever the power that is being produced inside, mechanical power, when it is coming out via the shaft, so the same power is not coming to the shaft or coming to the load. So when this power is coming via to the shaft, because of the friction in the bearings, because of the friction in the slip rings, the speed is decreasing. When the speed is decreasing, the output mechanical power is also decreasing. And at the same time, when the rotor is rotating, so there is an opposition to the rotor rotation due to that air friction, wind friction. So because of that, the speed is also reduced. So because of this reduction in speed due to that wind friction, reduction in speed due to the ball bearing friction, the reduction in the speed due to that slip ring friction, speed will decrease. When speed decreases, the output mechanical power also decreases. So that loss, we call it as a mechanical loss. I hope this point is clear. Confirm me. Confirm me. So can I say whatever the power that is being produced, mechanical power, 37, it is not coming out. When it is coming out, a part of the power is reduced due to the reduction in speed because of the slip ring friction, because of the ball bearing friction, because of the wind friction inside that air gap. So because of all this, the speed will decrease, the output power will also decreases, and hence there is some reduction in power. That loss, we call it as mechanical losses. Right? So how much is the loss here? Mechanical losses. So I'm writing mechanical losses as PML. PML, let us be 1 kilowatt. PML. So here I'm having P net or P shaft. P shaft. So here P net is the net power available at the shaft. P net is the net power. Net power. And PSH is the shaft power. Both are same. Shaft power. So this is equal to the internal mechanical power minus mechanical losses. So what is the internal mechanical power? 37. Let me assume that 1 kilowatt of electrical equivalent is wasted in mechanical losses, 1. So it is 36 kilowatts. So very finally, very finally, how much equivalent of electrical power is available as a mechanical power at shaft means it is 36 kilowatts of electrical power. But our intention is, as the stator has promised it to me, that 40 kilowatts of electrical equivalent is made available as a mechanical power at shaft. But very unfortunately, 4 kilowatts of power is been wasted. It is been thefted. It is been taken. So how much is the power that is taken? I mean loss, I mean to say, taken in stator circuit 2. How much is the power that is taken in rotor means 1. How much is the power taken by mechanical losses means 1. So the total is 4. Then how much is the electrical equivalent of mechanical is available at shaft means 36 kilowatts. Then what is the efficiency of this power flow? So efficiency of this power flow is P net by PSI into 100. So it is 36 by 40 into 100. You can see 90% of power flow. So what is the efficiency of this power flow? 90%. Is it clear? All of you confirm? Is it clear? Confirm? Right. See, whenever a question is asked, then you have to imagine all this. I'll repeat once again, just for a glance. So here our intention is to convert. So here what is the form? Mechanical form. So here what is our intention means to convert the 40 kilowatts of electrical power into mechanical. But very unfortunately, when that power is traveling, when that power is crossing the stator circuit, there is a loss in the stator circuit. That loss will be in the stator winding, and that loss is in the stator core. The loss in the stator winding, we call it as the copper loss. The loss in the stator core, we call it as core loss. And this core loss will be due to that eddy currents, the induced currents, and due to that hysteresis, the reversal of the dipoles. then the remaining power goes to rotor, right? So in the rotor, the losses are only in the winding, but it doesn't mean that the losses are not there in the core. But during running, the rotor frequencies are very less, SF. That is the reason the rotor core losses can be ignored. But if anyone questions, say the rotor is stationary, in that case, the rotor core losses can be ignored. No. Why? Because the rotor frequency at starting will be F. In that case, we cannot ignore. But we find out the efficiency only when the motor is operating, when the motor is rotating. So that is the reason we assume that the rotor core losses are neglected. Is this point clear? Confirm me. Confirm. Right. Then after that, the power is going to the rotor, and in the rotor there is some loss, and the remaining power is converted into mechanical. But very unfortunately, so inside who is rotating means the rotor core. Who is rotating means the rotor core. But the power which is being developed inside the rotor core has to be brought out. So who is bringing that mechanical power out means the shaft. But you know that shaft is passing through the ball bearings, and in case of slip rings and brushes, right? So whenever the shaft is passing through the ball bearings, there is a friction in that ball bearings. Due to that, there is some reduction in the speed. And as the brushes have been pressed on the slip ring, there is reduction in the speed. But whenever this rotor rotates, due to that wind friction in the air gap, there is a reduction in the speed. Because of all this, the rotor speed will be reduced. So due to the reduction in the speed, the output power is getting reduced. So that loss we call it as mechanical loss. So in this case, how much is the mechanical loss? Let us consider 1 kilowatt. Then how much equivalent of electrical power is available as mechanical at the shaft means 36, right? So like this, the power is flowing in the state in the induction machine. Is this point clear? Confirm me. Is this point clear? Confirm me, all of you. Right. So let me write some equations, then we proceed further. So here the stator output is equal to stator input minus stator losses. Similarly, the rotor output is equal to a rotor input minus rotor losses. Similarly, here P net is equal to the internal mechanical minus mechanical losses, right? So if I want to calculate the shaft torque, then what is the formula for calculating the shaft torque means? So shaft torque, just wait. So P net is equal to T shaft into omega R. So shaft torque is equal to P net by omega R, right? So it is P net by omega R means 2 pi nr by 60. What is that nr? Rotor speed in Newton, as rotor speed in RPM. Like that we can find out the so-called as P net, right? And shaft torque. Is it clear? All of you confirm me. Raise the hands once. Right. Just 1 second. See, Baba, some people are telling my voice is not clear. See, it is not my issue. So it is your issue. Why? Because I told you on my previous classes, if all are raising, then it is from my side. Then yesterday we have seen I have rectified. If 1 or 2 are raising means it is not from my side. You please try to understand it is from your side, right? Sir, increase the speed, sir, today, day 8. See, Baba, anonymous attendee. See, you have to keep one thing in the mind. See, I'm not here to complete the syllabus. I'm here to complete the subject. See, if I want to complete the syllabus, there is no need to go in detail and in depth, right? So you are facing a tough competitive examination, GATE and engineering service. So no one can expect from which area the questions will be raised. So remember, previously the questions were asked from a equation or from a formula, but those days are gone. Now, no question is directly asked from an equation or from a formula. So it is from the basics. So once you are clear with the basics, then you can answer any question. All right. So that is the reason we are going for this one. Right. Done. Right. So I'll stop. See, it is not the short notes, Baba. It is a clear notes only, right? So explanation is clear. So it is not a short notes. Please remember. See, one student, rotor core loss is less than the stator core loss. I told you that they are neglected, so we cannot compare. Right? Rotor core losses are almost neglected. We cannot compare. See, what are stray load losses? So we have not shown what are called as stray load losses. They are unwanted losses due to the changes in flux and due to the changes in winding resistance. We'll see lastly, right? No need to worry. See, my voice is not low, right? Please, Baba, you please check from your side, right? Done, right? Please. So this is something about your power flow. Is it clear? All of you confirm me? Confirm me. See, one thing, whatever I speak, if I want to write, so the time is not sufficient. So analysis will be more, writing will be just required what is required for you. I cannot write, so this is. If I do that, so not possible. Please try to understand. So I'll take some break. After that, I'll come back. Thank you. Okay. I'm back. All of you raise the hands if you can hear me. Right. Done. So the next and very important concept is the relationship between the rotor input power, the rotor losses, the rotor output power. Very, very important concept, right? Let us go for that. Relationship between the rotor input power, so I write it as P R I. Some textbooks call it as P1. We write PRY. Similarly, rotor losses. So whenever I talk about rotor loss, please remember it is the rotor ohmic loss. Core losses are neglected. And the rotor output power, that is PRO. So you know that the rotor input power can also be called it as stator output or air gap power. Similarly, the rotor output power can also be called it as the internal power or gross mechanical power developed. Right? We have seen that, right? Then we need to find out first the equation for rotor input, the equation for the rotor losses, the equation for the rotor output. Then we need to find out the relation. As I told you that we are going to find out all this using equivalent circuit. So whatever the parameter, whatever the equations we are going to derive should be in terms of this equivalent circuit parameters, right? So let us see what is it. Please see. So for that, what I'm trying to do means I'm trying to consider the rotor circuit. I'm considering a rotor circuit. So what is the rotor circuit? You already know. This is the rotor circuit. R2, JX2, this is E2, this is I2. For say, if I know the stator input power, if I know the stator input power, if I know the stator losses, then I can calculate stator output, which is nothing but the rotor input. Then from that, I can find out the rotor losses and I can find out the rotor output power, right? So, any issue? So is everything clear? All of you confirm me, is everything clear? Raise the hands once. Is everything clear? Raise the hands once, all of you. Right. So voice will build up, don't worry. Right. So everything is clear, done. So if I know the stator input, if I know the stator losses, then I can calculate the stator output as the stator input minus stator losses. Then from that we can find out the power for rotor loss and the rotor output. But fortunately or unfortunately, we don't know anything from this side. We don't know anything. So whatever we need to find out, so everything should be in terms of this rotor circuit parameters. How to find out? You please see. I'm having a source. I give one example from that. We'll learn something and we'll come back here. And the source is supplying some power, active power to a load. And I know the value of this resistance is 2 ohms. This current is 10 amperes. 10 amperes. So if anyone questions you, how much is the power supplied by that source to the load, means I don't know. Why? Because we don't have any measuring device on the source to find out what is the power that is being supplied to that load. Then I can tell in other way. What is that? As the value of that resistance is 2 ohms, so that is 10 square into 2. So it is 200 watts. As this load is consuming 200 watts of power, then I can say from this, the source would have supplied 200 watts of power to the load. So how much is the power that is supplied by that source? Means, can I say 200 watts now? So 200 watts of power is supplying to that load. Is this point clear? Is this point clear? All of you confirm me. Right. Similarly, which branch is consuming power in the circuit means resistance. Resistance. So if anyone question how much is the power that is supplied from source, that is stator to rotor, means I can say whatever the power that resistor consumes will be the power that is coming to that rotor. Why? Because I am talking about the active power, the true power. So whatever the power the rotor, the resistance consumes, that resistance consumes will be the power that is coming to the rotor. So that equivalent of power is coming to the rotor. I think this is clear. Confirm me, all of you. Confirm me, all of you. Raise the hands. Right. But the condition is, if I want to know what is the power that is consumed by the resistance, first of all, I have to see the frequency of this rotor circuit and the frequency of the stator circuit should be same. Right. Let us see what is the frequency of this rotor currents. If I take I2, so I2 is equal to E2 by R2 plus J X2. So if I simplify this, so it is S E2 naught by R2 plus J S X2 naught. If I simplify this, it is 4.44 SF phi R N2 KW2 by R2 plus J 2 pi SF into L2. Then I can say the frequencies of the rotor currents is not same as the frequencies of the stator current. How? As you can see from this equation, as the frequency of this E2 rotor voltage is SF, the frequency dependent parameter, that is X2, is also having a frequency of SF. So that is the reason this rotor current is also having a frequency of SF. But whenever I'm talking about this power that is coming to the rotor, I need the power which is coming to the rotor at a frequency of frequency of F. Why? Because, is my voice clear? All of you confirm me, raise the hands. See, Baba, I don't know. See, maximum people are raising the hands saying that my voice is clear, audio is clear. But few are raising the hands. Please try to rectify your network from your side. From your side, right? Please rectify from your side, please. From my side, it is clear. I'm clear from my side. Why? Because major of the students are saying that clear. So means it is from your side. Please try to understand, right? So what is the frequency of the rotor current? It is SF. Is it clear? Confirm me, all of you. Is it clear? Confirm me, all of you. But I want to know the power which is coming to the rotor when the frequency is F. So for that, what I'll try to do means I'll try to modify this rotor current in such a way that the frequencies of the rotor currents are same as the supply frequencies. But when we are trying to modify, the magnitude of current should not change. Why? Because if you remember, in case of transformer, basing on I2, the rotor current in transformer I'm talking, basing on I2, phi 2 will be there. Basing on phi 2, opposition will be there. Basing on that, change will be there. Basing on that, E1 will decrease. Basing on that, I1 will increase. Basing on that, power will increase. Who decides? Who decides the amount of power drawn from the source? Means the magnitude of current I2. So with respect to I2, the power will be drawn from the source. Is this point clear? Confirm me. Confirm me. Even in case of induction motor, who decides the power drawn means the rotor current I2. On what factor that rotor current will depend? Relative speed. Relative speed depends upon the load. If the load is not there, I2 will be less, opposition will be less, power drawn will be less. So if load is increased, power drawn will be more. So who decides that power drawn from the source or power supplied from the stator means the magnitude of I2. So when I'm trying to modify this to make the frequencies to be same, the magnitude of current should not change. Why? Because the current should remain same. So with that I'm modifying. See how I'm modifying this. I2 is equal to S E2 naught by R2 plus J S X naught. What I will do means I'll divide with S and I divide with S. So here S cancel, S cancel. If that is the case, it is E2 naught by R2 by S plus J X2 naught. Then if anyone questions me, or what is the frequency of this rotor current, means it is based on E2 naught. So what is the frequency of this E2 naught here? You can see F. The frequency dependent parameter X2 naught is also having a frequency of F. Then definitely the frequency of this current will be F. But calculating this I2 using this formula, or calculating I2 using this formula will give the same magnitude. There is no change in magnitude. But representing I2 using this equation will say the frequency is SF. Representing I2 using this will say the frequency is F. Right? So I need to modify the circuit in such a way that I have to find out the I2 using this equation. Right? How to modify that? Is this point clear? Confirm me. There's the hands. Right. Once again, I repeat. I want to calculate the power which is coming to the rotor. So in terms of the rotor circuit parameters. But when I want to find out the power which is coming to the rotor, I need the power at a frequency of F. First, I have taken the frequencies, the rotor circuit. Then it is found that the frequency of the rotor circuit is SF, but I don't want that. I have modified the equation. Then we seen that the rotor circuit frequency is F now. Why? As this E2 naught is having a frequency of F, then X2 naught is also having a frequency of F. This R2 by S is a resistor of resistance R2 by S, and your resistance is independent of frequency. So what is the frequency of this rotor current now? F. F. So calculating I2 here, calculating I2 will give the same answer. So there is no change in the calculation even if I modify the circuit like this, right? Now according to this, I'll try to modify the circuit. See here. So I'll be modifying like this. I2 J X2 naught. So if I calculate the current here, then the current is the same as your original circuit. So what is the frequency of this circuit? F. Is this point clear? First, we have modified the rotor circuit frequency as same as the stator frequencies. Raise the hands if it is clear, all of you. Right, done. Now, as I told you that which branch is consuming the power in the rotor circuit means resistance or resistor. So what is the value of that resistance? It is R2 by S. So whatever the power that fictitious imaginary resistance R2 by S is consuming, so that amount of power that will come to the rotor now. So can I say rotor input is equal to the resistance is R2 by S. The current flowing is I2 square, I2, assuming that it is three phase, it is 3 I2 square into R2 by S. Is it clear? Is it clear? Confirm. Right. Then I'll take a RL circuit like this. I'll take a RL circuit, RL circuit. The voltage is V, the current is I. If anyone questions you, Arey Baba, can you please tell me what is the equation for active power for that circuit? Yes. So P is equal to VI cos theta, where cos theta is equal to R by Z. Can I write that equation for active power like that? Can you please tell me? Can I write? Raise the hands. Raise the hands. Right. So the same equation I can write it as 3. What is the voltage to this circuit? E2 naught. What is the current flowing to the circuit? I2. What is the power factor of the circuit? Cos theta 2. So these two should be same now. Now let us see how they can be same. See, it is 3 E2 naught I2. So can I write cos theta 2 as R2 by Z? Already we have seen in the notations R2 by Z. So can I reshuffle this? How to reshuffle this? I'll just bring this Z2 here. So can I write 3 E2 naught by Z2 I2 into R. Just arranging, right? Is it clear? Confirm, all of you. Right. So what I'll do means, so here I multiply with S and I'll divide with S. I can do it. You know that this S into E2 naught is nothing but E2, and this E2 by Z2 is nothing but I2, and I2 into I2 is nothing but I2 square. I2 square. So tomorrow if anyone questions you, or what is the equation for the rotor input power, means it is 3 I2 square into R2 by S. R2 by S is not the rotor winding resistance. It is an imaginary fictitious resistance which is accountable for input power. So it is R2 by S. It is a fictitious resistance. Please remember that. So we are able to find out the equation for rotor input power. What is the equation for the rotor input power? This one. This is equation 1. Is this point clear? Confirm me. Confirm me, all of you. Right. Now we know that whatever the power that is coming to the rotor, the same power is not converted into mechanical power. A part of the power is wasted in the rotor circuit. Then what is the power that is wasted in the rotor circuit? It is in the winding. So what is that winding resistance? It is R2. So R2 by S is a fictitious resistance accountable for input. But what is the original resistance of the rotor winding? R2. So whatever the power that is wasted in that resistance R2 is the loss that is taking place in the winding. Is it clear? Confirm me, all of you. Confirm me, all of you. Right. See, Baba, one who are raising the hands in between. So from my side, there is no technical issue, right? 1 or 2 or up to 3, 4 means it is your side. It is not my side. Please make a note here. If bulk are raising, I'm rectifying the things. But as of now, no one is raising. So please try to rectify from your side, right? Then what is the equation for the rotor losses now? So rotor losses is equal to, what is the resistance of the rotor winding? R2. What is the current that is flowing? I2 square. I2, as it is a 3-phase, so it is 3 I2 square into R2. So this is the loss that is taking place in the rotor winding, right? Is it clear? Confirm me, all of you. Confirm me, all of you. Raise the hands. Right. Then how to find out the rotor output power means rotor output power is equal to rotor input power minus rotor losses. So rotor output is equal to rotor input minus rotor losses, right? So what is the equation for the rotor input? So 3 I2 square into R2 by S minus 3 I2 square into R2. Then I'll simplify this. If I simplify 3 I2 square into R2, if I take common, it is 1 by S minus 1. So this is the equation for the rotor output power. So tomorrow if anyone questions you, or I am having an induction motor in New Delhi, the resistance of the rotor winding is 0.1, okay. And the rotor windings are carrying a current of 10 amperes, okay. And the machine is operating at a slip of 0.4, okay. So can you please tell me what will be the input to the rotor? Yes, 3 I2 square into R2 by S. All values are given, calculate that. Can you please tell me the losses in the rotor circuit? Yes. Can you please tell me what is that gross mechanical power developed? Yes, 3I2 square into R2 by yes. So 3I2 square into R2 into 1 by S minus 1. Like that we can find out. Is this point clear? Confirm me. Is this point clear? Confirm me. Right. So this resistance I call it as a load resistance. 3I2 square into RL, where RL is equal to R2 into 1 by S minus 1. This I call it as a load resistance. Why I'll be calling it as a load resistance, right? Please see. Now I'll modify something. After that I'll come back. See, can I take R2 by S like this? R2 by S. I will add one R2 and I'll subtract one R2. Can I do it like this? Please confirm me. Confirm me. Right. So I'll rearrange this. How I'm rearranging? R2 plus R2 by S minus R2. So this I can write it as R2 plus R2 into 1 by S minus 1. So can I say this R2 by S, I can split it into two parts. What are those two parts? This R2 by S, I can split it into R2 plus R2 into 1 by S minus 1. Can I split? Confirm this? Can confirm me? Confirm this? Right. So splitting that, I'll draw the rotor circuit. I'll draw the rotor circuit. Let me draw the rotor circuit. So here, the first part of that resistance is R2, and this is J X2 naught, and the other part of that R2 by S is R2 into 1 by S minus 1. Right? Is it clear? Can I modify the circuit like this? Confirm me. Confirm me, all of you. Yes. So in this, what are the fixed values? You can see what are the fixed values. E2 naught is fixed. Why? Because it is the rotor voltage at standstill, which is fixed. This is fixed, and this is also fixed. So this R2 is accountable for the ohmic losses. X2 naught is accountable for the reduction in power due to leakages. Then what is this R2 into 1 by S minus 1 represent? This represents the load resistance, and this is a variable branch. On what basis I'm calling it as a variable branch means, as with the load, the speed changes. With the speed, the slip changes, and with the slip, this branch R2 into 1 by S minus 1 will also changes. So that is the reason it is called as a variable branch. Why I'm calling it as a load resistance? See, already I told you that what is an equivalent circuit? What is an equivalent circuit means? It is the electrical circuit representation of a physical machine. So the machine is represented in terms of RLC branches. Now, if you consider any machine, motor, and the motor load will be there, and that load has to be represented in equivalent circuit. So by which branch we are representing that mechanical load in the equivalent circuit means with this R2 into 1 by S minus 1. Y means C. If the motor is running without load, when the motor is running without load, then the rotor speed will be closer to ns. When the speed is closer to ns, the slip will be approximately equal to 0. When the slip is approximately equal to 0, R2 into 1 by S minus 1 will be approximately equal to infinity. That means this load resistance will act as a open circuit, almost open circuit. When it is acting as an open circuit, the rotor current will be very less. The rotor input power will be very less. Why the rotor power will be very less means, as there is no load, then the required rotor power will be less. This is balanced like this. But whenever you are increasing the mechanical load, then immediately what happened to the speed decreases. What happened to the slip increases. Then what happened to this resistance R2 into 1 by S1, as slip is increasing, this load resistance will decrease. When the load resistance is decreasing, the current drawn by the rotor circuit will increase, the power drawn will increase, the torque will increase, and the torque is supplied to that load. Like that, with the mechanical load, when we are changing the mechanical load, which branch in the rotor circuit will change means R2 into 1 by S minus 1. So that branch we call it as a electrical equivalent of the mechanical load. So tomorrow if anyone questions you, or we are representing a induction machine electrically. So you have represented the rotor ohmic losses as R2, the power reduction due to leakages as X2 naught, and how you are representing the load on the motor, the mechanical load on the motor means with the equivalent resistance R2 into 1 by S minus 1. So this is the mechanical load. So tomorrow if anyone raises a question, or how you are representing a mechanical load in the equivalent circuit means with a resistance whose value is R2 into 1 by S minus 1. Is this point clear? Confirm me. So can I write like this? R2 into 1 by S minus 1 is the electrical equivalent of the mechanical load placed on the rotor shaft, right? So this question was asked many times, right? So what does that means? Which is the branch representing the mechanical load means R2 into 1 by S minus 1 represent the mechanical load. Is it clear? All of you confirm it? Raise the hands. All right. So tomorrow if anyone questions you, or I am giving the value of R2 to you, okay, I2 to you, okay, C to you, okay. Say you have calculated 3 I2 square into R2 into 1 by S minus 1. Let it be something like 37 kilowatts. The value to be 37 kilowatts. What the meaning of the 37 kilowatts means? I don't know what is the power you are giving to the rotor stator. So we don't know what is the power you are feeding to the stator. But out of that power, only 37 kilowatts of electrical power is converted into mechanical power. So can I say which power or which branch power is representing the mechanical power means whatever the power the branch R2 into 1 by S minus 1 is consuming, that amount of electrical power is converted into mechanical power. So that amount of power is converted into mechanical power. Is this point clear? Confirm me all of you. So I'll redraw this circuit again. So can I draw like this? So it is R2 J X2 naught. This is R2 into 1 by S minus 1. This is E2 naught. This is I2. So what is the equivalent resistance here at the input R2 by S? What is the rotor resistance R2? What is the load resistance R2 into 1 by S minus 1? So if anyone questions you, or what is the power to the rotor circuit, whatever the power this resistance R2 by S is consuming, what is the power that is wasted in the rotor circuit, whatever the power this resistance is consuming R2, or how much is the power that is converted into mechanical power, whatever the power that R2 into 1 by S minus 1 is consuming. Is this clear? Confirm me. Is it this clear? Confirm me all of you. Right. Now I want to find out the ratios. What is that ratio? I need to find out the rotor input power by the rotor output power. So what is that equation for the rotor input power? You have already can see it is 3I2 square into R2 by S. So you can refer that slowly. So it is 3I2 square into R2 by S. What is the equation for the, let me calculate rotor losses first. What is the equation for rotor losses? 3I2 square into R2. So here you can see this 3I2 square R2, 3I2 square R2 will get cancelled. So here I'll be having 1 by S. So it is equation 1 by equation 2. Similarly, if I calculate or if I find out the ratio rotor losses by the rotor output, it is equal 2 by equation 3. The rotor losses are 3 I2 square into R2 by 3 I2 square into R2 into 1 by S minus 1. If I simplify this, it is S by 1 minus S. Similarly, if I want to find out the rotor output by rotor input, if you do that, so it is 3 by 1, then I'll get 1 by S by 1. Then finally, what is the relation we are having? Rotor input, rotor losses, rotor output is equal to 1 is to S is to 1 minus S. So this is a very big relation in induction motor. Very, very important relation. And basing on that, we have many equations, many numericals. Please remember, the left-hand side sequence is important. Basing on the right-hand side sequence is important. It is not like always the right-hand side sequence is 1 is to S is to 1 minus S. So this is 1 is to S is to 1 minus S only when the left-hand sequence is input losses and output. Recently, in one of the competitive examination on the left-hand side, the sequence was rotor input, rotor output, rotor losses. If so, on the right-hand side, 1 is to 1 minus S is to S. So please remember this. Is this point clear? Confirm me, all of you. Right. So as of now, if anyone questions you, are you are not having a physical motor? Yes. You are having only rotor circuit parameters. Yes. What are those rotor circuit parameters? E2 naught, I2, R2, yes, like that we are having rotor circuit parameters. Yes. So can you find out the rotor input power without the physical machine? Yes. It is 3 I2 square into R2 by S. So can you find out the rotor losses? Yes. Can you find out the rotor output power? Yes. So as of now, basing on the rotor circuit parameters, I can find out the rotor side values. What is it? Rotor input, rotor losses, rotor output. Is this clear? Confirm me, all of you. Is this clear? Confirm me, all of you. Right. Next, observations. We'll see one or two observations today. Observations. So what are those observations? Let us see. Observations. So what are those observations? First one is, I'll take this relation. Which relation? Rotor input, rotor losses, rotor output. I'll take this relation. Just wait. Yes, bulk response. So it is like drizzling outside. Just wait. Now audio is clear. All of you confirm. Raise the hands. Audio is clear now. Raise the hand. No, just wait. I'll come. Now it is clear. Audio is clear now. Please raise the hands. Right. Done. Fine. Now I'm trying to look into this. So it was like storming, thundering. That is the reason some interference would have happened. But anyhow, so I want to go for first observation, the rotor efficiency. Rotor efficiency. It is raining heavily, but I made all the arrangement. If any power cut is there, that UPS, everything I have made arrangement. Why? Because there should not be loss of class, right? Rotor efficiency. What is the formula for rotor efficiency? It is the rotor output by the rotor input. Rotor output to the rotor input. So from this, what is the equation for rotor output to the rotor input? 1 by S minus 1. 1 by S my 1 minus S by 1, right? 1 by 1 minus S by 1. So if you remember the definition for slip is equal to Ns minus Nr by Ns. This I can write it as 1 minus Nr by Ns. So from this, Nr by Ns is equal to 1 minus S. So even this will be NR by NS. So from this, what is that observation you can see? The rotor efficiency depends upon the rotor speed. If the speed is very less, the rotor efficiency is very poor. And if the speed is closer to NS, the rotor efficiency will be very, very high. I take one example from that we can imagine. See, let me consider it is a 6-pole motor excited with a 50 hertz supply. Then what is the synchronous speed in this case? Synchronous speed is equal to 1000 RPM, 120 into F by P. Let us see the rotor speed is 10 RPM. And let us see the rotor speed is 10 RPM, say. Then using that relation, what is the rotor efficiency? Rotor efficiency is equal to NR by NS into 100. So it is 10 by 1000 into 100. So it is how much? 1%. You can see the rotor efficiency is only 1%. When the rotor speed is away from synchronous speed, the rotor efficiency will be very, 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 very poor, right? Now, if I take the same rotor speed is equal to say 990 RPM, say, then you can see the rotor efficiency will be 99%. 99%. Can you see this numerically? Is it clear, all of you? Numerically, is it clear, all of you? So can I say like this? If the rotor speed is very closer to synchronous speed, the rotor efficiency will be very high. And if the rotor speed is away from synchronous speed, the rotor efficiency will be very, very poor. Then what is the reason for that? What is the reason for that? If the rotor speed is very closer to synchronous speed, the relative speed is very less. It is 1000 minus 990. It is only 10 RPM. That EMF will be less. The currents will be less. The ohmic losses will be less. When ohmic losses are less, whatever the power that is coming to the rotor, majorly it is converted into mechanical. Why? Because the losses are less and efficiency will be very high. But if the relative speed is more, 9,000 minus 10, 990, the flux cuttings will be more, EMFs will be more, currents will be more, ohmic losses will be more. So whatever the power that is coming from stator to rotor, majorly it is wasted in the rotor circuit, partially it is converted due to mechanical. That is the reason the efficiency will be very less. So for that reason, you can see whenever you are designing an induction motor, you have to design in such a way that the rotor speed should be always closer to synchronous speed. So even the motor is running without load, or even the motor is fully loaded, the rotor speed should be closer to NS. But with the load, if the rotor speed is coming away from NS, then the machine will operate with poor efficiency. So that is the reason the manufacturers are designing the induction motors in such a way that when the motor is fully loaded or if it is not loaded, the speed has to be closer to NS so that the rotor efficiency is high and overall efficiency is also high. So that is the reason if you look into this induction motor, the rotor speed will be very closer to NS. So for that, the slip ranging should be very, very less. Is this point clear? Confirm me. So can I write like this? The rotor efficiency depends on the rotor speed. A rotor speed. If the induction motor is operated with the speeds away from synchronous speeds, the rotor efficiency will be very less. To maintain the rotor efficiency, the rotor speed should be closer to the synchronous speed. Synchronous speed. Is this point clear? Confirm me all of you. Confirm me all of you. For this, the induction motors are designed for the slip ranging from 2 to 8%. 2 to 8%. But what is the full range of slip? 0 to 100%. That means we have a full range of 0 to 100% for induction motor. But very unfortunately, what is the operating range? It is less than 10%. So we need to operate the induction motor in very low range of slips, less than 10% for a efficient performance. For a good performance, that speed should be always closer to NS. So this is a very, very important question. In most of the interviews, this question was raised. What is that question? Why the induction motors are designed for the speeds closer to NS? Then you can see if the rotor speeds are away from synchronous, so the flux cuttings in the rotor conductors will be more, the EMFs will be more, the currents will be more, the ohmic losses will be more. So most of the power which is coming to the rotor will be wasted in the form of heat, and hence the rotor efficiency will be less and overall efficiencies are also very less. For that, the induction motors are always designed for the speeds closer to NS, even though we are having a very wide range of slip, 0 to 100%. So we don't operate the machine in a very wide range of 0 to 100. So for a good performance, for a better performance, for excellent performance, the slip should be from 2 to 8%. It is less than 10%. Is this point clear? Confirm all of you. Confirm. Basing on this, there was a question recently asked, right? Recently, some 5-6 years before. So what was that question? Means, see, the rotor speed of a 3-phase induction motor is 60% of synchronous speed. What is the approximate motor efficiency? What is the approximate value of motor efficiency? Motor efficiency. See, there is no like formula to calculate the motor efficiency. It's only this information is given. So for calculating the motor efficiency, you have to follow the sequence. What is that? The stator input will be given. You have to subtract the stator losses to get the stator output. Then you have to subtract the rotor losses to get the rotor output. Then you have to subtract the mechanical losses to get the net power. From that, you have to find out the ratio to calculate the motor efficiency. That is the flow. That is a sequence, right? But very unfortunate, with only synchronous speed, rotor speed is given, and he's asking the motor efficiency. So in that case, you have to approximate that motor efficiency is equal to rotor efficiency. Why? Because there is no other information given. So in this case, I'll be approximating the motor efficiency as the rotor efficiency. It is only for the numerical value. Only for the numerical values. But truly speaking, it will not happen. It is only for numerical value. So it is approximately NR by NS into 100. If that is the case, how much it is? 60%. So for example, say if the options are given like 60, 70, then 80, then 90, then what is the answer in this case? 60. Like that you have to answer. But say if there is an option which is given 50, less than 60, if any option is given, then in that case you have to take less than 60. Why? Because the overall efficiency will be less than the rotor efficiency. I hope this point is clear. Confirm me all of you. Confirm me all of you. Right. So this is something about your observation 1. So we have still more. So as it is already 8:35 or 8:36, I'll stop for today. Why? Because we need to have a doubt session also. So if I continue means, so the time will cross more than 9, right? So most of the people, some students have class tomorrow morning also. That's the reason I cannot proceed further. I'll stop for now. So we'll have doubt session. After that, we'll see. Just give me 2 minutes. I'll get that. Right. Let me see any question in this. So the rotor speed will be always rotating with a speed closer to ns. Why? Because to obey Lenz's law. Already I told you. So what is the overall efficiency of a induction motor? It is around 90 to 92% roughly. Why? Because the leakage reactance represent the reduction in power due to leakages. So this leakages depends upon the current flow. When a coil carries current, there will be magnetic flux lines. Then those number will be depending upon the amount of current. That is the reason it is a series. Sir, higher the load, higher the slip. No, higher the load, lower. Yes, it is closer to yes, higher the slip. Then what all can we do to make sure that machine operates closer to that ns? See, always we need to design in such a way that the rotor speed should be closer to ns. So the manufacturer will take care of all those things. So he'll be designing in such a way that when the machine is under no load condition, the speed is very closer to that. So when the machine is away, when the machine is fully loaded, it is slightly away from that, but so it will not be coming far away from that, right? Right. See how the resistance value is more at running compared to initial. So here R2 is fixed, but X2 naught is variable. At starting, X2 naught is very high, but once the motor starts rotating, as the slip value decreases, SX2 naught will start decreasing. When SX2 naught starts decreasing, the resistance value start dominating, right? Please. Right. I'll come back to this questions and answers now. So raising hands. Right. Hemalata. Hemalata. You are there, ma? I think no. Right. Next. Hello. Bhavani. Hello. See, she is also not there. Hello. Sai Charan Reddy.
Hello, sir.
Yeah. What happened yesterday? You didn't ask any doubt. Sai Charan Reddy. You are not there.
Sir, yesterday I went to hospital, sir. That's why I did not attend the class.
What happened? You are okay now? You are fine?
Okay, sir. Okay.
Is there any
Hello, sir. Yeah, sir. In yesterday,
Yeah, please.
sir.
Yeah. Please carry on with the
Sir,
question.
today all is clear, but yesterday's doubt in an example you took f is equals to 2 minus f2 is equals to 2 minus s into f now, sir.
It is not the question. It is
In
something.
that,
Yeah, please, Sai Charan Reddy.
okay, sir. Anand.
Yeah.
Sir, in that 2 minus s means in that slip we should take ns plus nr or ns minus nr, sir, for that slip.
See, actually, by definition, slip is ns minus nr by ns.
Yes, sir.
Okay, right?
Yes.
But when you are changing the phase sequence, then what happened to the direction of the feed?
Reversed.
Then what about the relative speed between field and the rotor conductors?
ns plus nr.
So the relative speed increases to ns plus nr, right? Then
Okay.
what will be the frequencies of the rotor current now? The relative speed into P by 120.
Yes, sir. Yes, sir.
Now, if I modified that ns plus nr, so can I write that ns plus nr as 2ns minus nr? Can I write?
Okay, sir. Okay, sir.
Then if I
2ns.
can I simplify like this? So finally, can I write 2 minus s into f? Can I write? So what I mean to say is, when the phase sequence is ABC, say the direction of the field is clockwise, then the rotor is also rotating clockwise, then the frequencies of the rotor currents will be s into f.
Yes, sir. Yes, sir.
When you are changing the phase sequence to ACP, then the frequencies of the rotor currents will be changed to 2 minus s into f, where s is the previous value of slip.
Yes, sir. That's my doubt, sir. Yes, sir. Okay, sir.
Now you are clear, Sai Charan Reddy?
Yes, sir. Yes, sir. Clear, sir.
Right. Any more doubt?
Okay, sir. Sir, here back EMF means that will be in relation to load. According to your today's class,
Yeah, please
I
ask.
I got
Yeah,
an idea that if we change the load, like if we add some weight to the shaft, then the E1 will also change it. E1.
yeah. So whenever you are changing the load, then the load demands more mechanical power, right?
Yes, sir. Yes, sir.
So when the load demands more mechanical power, the machine has to draw more electrical power, right?
Yes, sir. Yes, sir.
So what is the communication, that how the load will communicate to the source that I need more mechanical power, you supply more electrical power. How means? So whenever you are loading, what happened to the speed?
Decreases, sir.
What happened to the relative speed?
Increases.
The flux cuttings,
Increases.
the I2,
Increases.
the flux magnitude, rotor flux magnitude phi2,
Increases.
opposition.
Increases.
Then what happened to the resultant flux at that instant?
Decreases.
Then what happened to that E1?
Even also decreases.
V minus E1,
Increases, sir.
current drawn,
Increases.
power drawn,
Yes. Increases. Yes, sir. Yes, sir.
power fed to the rotor,
Increases.
output of the rotor,
Increases.
the mechanical power fed to the rotor, that
Increases, sir.
shaft.
Shaft is increased.
Now clear?
Okay, sir. Okay, sir.
Right, Baba. Right?
Yes,
Okay.
sir. Yes, sir. Perfect, sir.
Right. Okay, Baba. Right. Right. Bhaskar.
హలో సార్
Ha, Baba. Please.
సార్ ఇక్కడ రోటర్ సర్క్యూట్స్ కి ఒక డిఫరెన్స్ చెప్పారు ఏంటి సార్ అది ఫ్రీక్వెన్సీ అని
ఏం లేదు నాన్న. ఇప్పుడు see. If I take this rotor circuit, ఇది కాదు, this rotor circuit, what is the frequency of the rotor current?
ఎఫ్ సార్
SF.
ఎస్ సార్
But I సో అదేదో తగ్గి, అది దాంట్లో తగ్గి సార్, జాగ్రత్తగా విను. సో ఐ వాంట్ టు నో ద పవర్ దట్ ఈస్ కమింగ్ టు ద రోటర్ అట్ ఎ ఫ్రీక్వెన్సీ ఆఫ్ ఎఫ్. అవునా? ఎందుకంటే మన స్టేటార్ కి నౌ వాట్ ఎవర్ ద పవర్ యూఆర్ సప్లైంగ్ టు ద స్టేటార్ ఈజ్ అట్ ఎ ఫ్రీక్వెన్సీ ఆఫ్ ఎఫ్, కరెక్ట్?
ఓకే
So I need that power which is coming to the rotor. Then I have to modify the rotor circuit in such a way that the rotor frequency should be same as the stator frequency. So then for that I have modified the rotor circuit. Even after the modification, the current I2 should not change. So this is the equation for the rotor current indicating the frequencies are SF. This is the equation for the rotor current indicating the frequencies F. But if I calculate the magnitudes in both the cases, the magnitude will remain same. So I can modify the circuit like this. So for that I have modified the circuit like this. Is it clear, Bhaskar, now?
ఓకే సార్ అంటే ఫస్ట్ సర్క్యూట్ లో ఎస్ఎఫ్ అనే ఫ్రీక్వెన్సీ ఉంటుంది అంతే
Antena. That's all. Okay.
ఓకే థ్యాంక్ యూ సార్
Right. Bhaskar. Shraddha.
Hello, sir.
Hama, please. Shraddha.
Sir, what will be the direction of rotor field?
So in which case,
Yesterday's class.
Suppose, yes, sir. If stator field is moving in clockwise direction, then rotor field will be also in clockwise direction, right?
Absolutely in the clockwise direction. Why? Because who is responsible for EMF in the rotor circuit?
Stator field only.
If the stator phase sequence is A, B, C, say clockwise, then in which direction the EMF will be induced? In the clockwise, A, B, C only, right?
Okay.
First, A phase will be having the positive peak, followed by B phase, followed by C phase, right?
Okay.
Then,
Sir, yeah, but if stator phase sequence is changed, then rotor phase sequence should also be changed, right?
yes, rotor phase sequence will also be changes. That is the reason the relative speed between the two fields will be zero. Then only the rotor will be rotating in opposite
Yeah,
direction.
to satisfy Lenz's law. Yeah.
Yes, absolutely correct. Understood.
But first, if stator phase sequence is changed, then rotor will take some time, right? It will go under deceleration and then it will change its phase sequence, right?
Yeah, obviously, the direction of the field will be reverse, and
Yes.
the direction of rotor will be reverse.
Yeah. And what will be the direction of resultant field? It will be also same direction.
Yes.
Resultant field.
Yeah, it will be in the same direction as your. See, whatever the direction, the rotor has to rotate in the same direction. The field will also act. So, in the same direction of the stator field, the resultivity lacks. Why? Because so
Yeah.
who is making the rotor to rotate? The resultant. So the rotor which was rotating clockwise, now it is supposed to rotate in counterclockwise. So in which direction the resultant field will be acting? In opposite direction, in counterclockwise only. That's the reason the rotor will slow down in clockwise, reaches to zero, and it will rotate in counterclockwise direction. Resultant will be in counterclockwise direction. Is it clear, ma?
Yes, sir. Yes, sir. Thank you.
Right. Shiva J.
Sir, good evening, sir.
Good evening, Shiva J. Yeah,
Sir,
please.
can you explain that leakage reactance one more time?
So today's class or previous class?
Yes, sir. Today's class, sir. You explain
See,
leakage reactance.
yeah, I'll explain. See, every coil will be having some inductive nature, right?
Yes, sir.
So if I take a rotor winding, it is nothing but a coil.
Yes, sir.
So that coil will have some inductance. Is it clear?
Yes, sir.
At the same time, so when the magnetic field lines are traveling from stator to rotor, some of the flux lines are leaking, right?
Yes, sir. Through
When
air
the-
gap.
yeah, so some of the flux lines are completing their path within the stator or rotor only. So they are not linking both,
Okay, sir.
right? Due to that leakages, what about the amount of power transferred?
Less, sir.
Less. That means if I'm treating the rotor circuit as a resistive load, then whatever the power that is coming from stator has to reach the rotor, correct?
Yes, sir.
But it is not happening here due to the self-inductance of the coil and due to the leakages, a part of the power is going to be reduced, correct?
Yes, sir.
So there has to be one more branch which is responsible for accounting all these things. Reduction in power due to that leakages, right?
Yes, sir. Yes, sir.
So that branch I'm representing like a leakage reactance branch. Is it clear now?
Yes, sir. Okay.
Understood, Shiva?
Yes, sir.
Right. Okay.
Thank you.
Okay. Bhavani. Bhavani.
Good evening, sir.
Good evening, ma'am.
Sir, my doubt is from yesterday's class, sir.
You can ask yesterday's class, but not tomorrow's class. Yes, you can ask.
Sir, for the actually, my thought is like for the rotation of a rotor, two actions are two actions అక్కడ రీజన్ అవుతున్నాయి సార్. ఫస్ట్ ఏంటంటే పోల్స్ కి నార్త్ అండ్ సౌత్ పోల్స్ కి am I audible, sir?
Yeah, ma, you are audible. Yeah, I'm listening to your question. Cheppamma.
పోల్ అదే రోడ్ స్టేటర్ అండ్ రోటర్ పోల్స్ మధ్యలో ఇంటరాక్షన్ వల్ల రొటేట్ అవుతుంది. ఇంకోటి ఏంటంటే రోటర్ వైండింగ్స్ లో ప్రొడ్యూస్ అయ్యే ఫోర్స్ వల్ల రొటేట్ అవుతుంది సార్.
Chudamma, see, the first answer is only correct. See, it is not the force, to be honest enough. So the core is acting as a magnet here, correct?
Yes, sir.
Why the core is acting as a magnet here? Why? Because whatever the windings you are placing on the rotor core, so because of those current, so the dipoles which are inside that will be like aligning, and because of that there is some pole formation, right?
Yes.
So this pole formation, this magnetic field, and the flux lines due to that current carrying conductor will be resulting in the total pole formation. So that is the reason when I was drawing about the concept of rotor poles, you can see I have taken two conductors and we have find out the individual flux loop. Then after that we have taken the resultant flux loops. Because of this resultant flux loop, all the poles are formed. So this everything will set up the rotor flux. You are not supposed to take the flux due to current carrying conductor, the flux due to pole as separate. You have to mix up and you have to call it as rotor field or rotor flux. Understood, ma Bhavani?
ఎస్ సార్ ఇంకోటి ఏంటంటే ఈ రోటర్ ఫీల్డ్ వల్ల ఈ రోటర్ ఫీల్డ్ స్టేటర్ కండక్టర్స్ ని రియాక్ట్ కావా సార్ ఈ ఫీల్డ్ వచ్చేసి
That's what Amma. See, that's what I told you that. So at steady state, you don't find stator field, you don't find rotor field. You feel only one resultant field. So finally, which flux lines are cutting both the conductors? Neither stator nor rotor. Only the resultant field lines will be cutting. Understood? You cannot find these two. Only one flux will be finding in the air gap finally. Which flux will be finding? The resultant field. That field will be cutting the stator conductor and this field will be cutting the rotor conductor. That is the only field cutting. So if I talk separately, then the total concept will go. No separate. It is only one field. Now clear, Bhavani?
ఎస్ సార్ వన్ మోర్ డౌట్ సార్
Yeah.
సార్ మీరు స్క్వేరల్ ఫీచర్స్ ఆఫ్ స్క్వేరల్ కేజ్ రోటర్ లో థర్డ్ పాయింట్ మనం ఇక్కడ బార్స్ యూజ్ చేస్తున్నాం కానీ వైండింగ్స్ యూజ్ చేసినట్టు టూ ఫేజ్ లాగా ప్రొడ్యూస్ అది మనం కన్సిడర్ చేస్తామని ఒక డయాగ్రామ్ గీసారు సార్
నేను చెప్పింది ఏంటంటే జనరల్లీ ఇన్ కేస్ ఆఫ్ ఎ స్క్విరెల్ గేజ్ we don't have any windings, right?
yes
Unlike the stator, we are not placing any windings. But what is
Yes.
that? We are placing bars, right?
bars
But only for on paper calculation, for a mathematical calculation, if you want to treat how many rotor phases are there, means there is one formula, there is one thumb rule, which is like the number of rotor phases can be the number of bars per pole. It is only for on paper calculation, but truly speaking, there will not be any phases in the rotor circuit. Understood?
సార్ మీరు ఈఎంఎఫ్ క్రియేట్ అవుతుంది అంటే టూ కండక్టర్స్ లో ఈఎంఎఫ్ క్రియేట్ అయితే టూ కండక్టర్స్ లో అబ్సెంట్ ఉంటది అన్నారు సార్
అంటే
ఇప్పుడు
అడగ
సి కండక్టర్ లేటెస్ట్ టేక్ సి కండక్టర్ నార్త్ పోల్ అండర్ నార్త్ పోల్ వచ్చినప్పుడు మాక్సిమం ఫ్లక్సెస్ కట్ అవుతాయి కదా సార్ ఈఎంఎఫ్ క్రియేట్ అవుతుంది కదా సార్ అలాగే ఏ కండక్టర్ మళ్ళీ సి ప్లేస్ లోకి వెళ్ళినప్పుడు కూడా సేమ్ ఈఎంఎఫ్ కట్ అవుతాయి కదా సార్
అవునమ్మా ఇప్పుడు అది మూవ్ అవుతుంది అనుకో ఆ పొజిషన్స్ ఆఫ్ ద పోల్స్ మారుతుంటాయి కదా అంటే ఏదైతే రెండు కండక్టర్ల మాక్సిమం వోల్టేజ్ ఉందో ఈ పోల్స్ మూవ్ అవుతున్నప్పుడు ఈ వోల్టేజెస్ జీరో అయిపోయినప్పుడు ఈ వోల్టేజెస్ మాక్సిమం అవుతాయి అంటే వాటి మధ్య ఫేజ్ షిఫ్ట్ ఎంత ఉన్నట్టు స్పేషియల్ గా 90 degrees అంటే ఎన్ని ఫేజెస్ ఉన్నట్టు నీకు దాంట్లో
2 phases
అలాగా బేస్ చేసుకొని చెప్పాలమ్మా అర్థమైందా ఎప్పుడైతే ఈ పీక్ వాల్యూస్ మారుతి దానికి వస్తున్నాయో అంటే ఈ వోల్టేజెస్ ఏమైపోతాయి నీకు జీరో అయిపోతాయి కదా ఇది నార్త్ పోల్ సౌత్ పోల్ అనుకున్నామ్మా ఈ రెండు కండక్టర్స్ లో మాక్సిమం అనుకుందాం ఎప్పుడైతే ఈ పోల్స్ ఇక్కడికి వచ్చినాయో ఈ రెండు కండక్టర్స్ లో వోల్టేజ్ మాక్సిమం అవుతుంది అంతే కదా అప్పుడు ఈ వోల్టేజెస్ ఏమైపోతాయి జీరో అయిపోతాయి అంటే ఇప్పుడు ఈ ఫోర్స్ వోల్టేజెస్ మాక్సిమం అయిన ఈ ఫేజ్ వోల్టేజెస్ జీరో అయిన అని అర్థం అర్థమైందమ్మా
అర్థమైంది
రైట్
అంతే సార్
రైట్ నా
థాంక్యూ సార్
Pratyush.
Sir?
Yeah, Pratyush.
Sir, you have said that leakage reactance is account for the power loss, no, sir?
No, I never said power loss, reduction in the power. See, if I'm having a supply, the supply has the capacity to give 1000 VA.
Okay,
understood,
sir.
right? So, if the power factor is say very poor, say if it is only 0.1, how much power it is drawing? 1000 into 0.1, it is drawing.
100, sir, yes.
Right? So if the power factor is good, say 0.9, how much it is drawing? 900 it is drawing.
Yes, sir.
Now who is reducing the power drawn from the source? The power factor. If
Yes, sir.
for the same 100 VA, so if the power factor is very poor, it is forcing to draw less active power. If the power factor is more, it is forcing that more active power to draw. Right? Who is deciding that power drawn? The power factor. So who is reducing the power from the source? It is a power factor. The active power, who is reducing? The power factor. So the power which is coming to the machine, and from that a power is wasted in the windings. So that is a loss. So first, who is opposing the power? The power factor. After coming, who is reducing the power? The losses. I hope you understood this.
Yes, sir. Sir, in case of transformer, those leakage reactance are account for the voltage dip, no, sir.
See, it is not the voltage dip. You have to tell it is something like drop. So it is not
Yes,
a dip.
sir.
Understood?
Yes, sir. Voltage drop, sir. Is the same doesn't account for this induction machine, sir.
There also voltage drop. There also it is something like reduction in the active power. See, if your secondary circuit is highly inductive,
Yes, sir.
then the nature of that power drawn from the source will be more reactive power compared to your active power.
Yes, sir.
Understood? So when the circuit is highly inductive, then it is drawing more reactive power compared to active power. So everywhere it is accountable. It is not only in induction. Please remember that. Understood?
Okay. Yes, sir. Okay, sir. Thank you, sir.
Right.
Hello, sir.
Kumar.
Sir, in the statement of when the starter winding is closed, short circuited.
Not starter, stator winding. Kumar.
Yes.
Yeah.
Yes,
Ha,
sir.
Baba.
If a three-phase supply is given to rotor,
I
there is
told
one kind.
already. I told you yesterday. I think you are not there during that time. So anyhow, I'll explain this in the coming days. Don't worry. So as of now, for this, the answer is if you are giving the excitation to the rotor winding, right? Keeping
Yes.
that stator winding short circuited, then the rotor will rotate in a direction opposite to the field. Say if the rotor field is rotating clockwise direction, but the rotor will rotate in opposite direction. So you can analyze the same thing from the basics which we have discussed in the yesterday's class. Still, if you are not getting, anyhow, I'll explain this in the coming days. But as of now, you can just make a point. The rotor will rotate in a direction opposite to that rotor field. Is it clear?
Okay, sir.
Right.
Thank you, sir.
Right. Some PC. Who is that PC?
Hello.
Ha, Baba. PC.
Sir, sir, one question asked in the interview. You said that
Yeah. Please
while
ask.
designing induction motor,
Mhm.
always NS is closer to NR.
The rotor speed should be always closer to NS.
Yes, sir.
Right? If the
Yeah.
rotor speed is away from NS, then what will be the relative speed between field and conductors?
0.
Increases, na?
Increases.
Yeah. Say if the rotor synchronous speed is 1000, the rotor speed is at 10. The relative speed will be very large.
Yes, sir.
Then flux cuttings,
Flux cutting also large.
large. When the flux cuttings are at EMF,
Increases.
currents,
Increases.
ohmic losses,
Sir, on classes increases.
right? Then whatever the power that is coming to the rotor, majorly it is wasted in the rotor circuit. Why? Because the losses are more. Then power conversion will be
Sir, more.
less.
Less,
Lesser.
sir. Less.
Right. Then rotor efficiency will be
Less.
overall efficiency will be.
Overall is also less.
For that, the rotor speed should be closer to
NS.
NS. That is the answer for that. Understood? PC.
Thank you, sir.
Right, Baba. Right. Bhavin.
Hello, sir. Hello. Am I audible?
But huge noise.
Yes, sir. 1 minute, sir.
Ah.
Sir, now am I audible?
You are audible, but behind there is a background.
Sir, just give me a minute, sir. I will switch off the fan.
Yeah, please.
Hello, sir. Now is it clear?
Absolutely clear.
Sir, yesterday while explaining the concept of rotor speed,
Mhm.
sir, you said that you explained like this that the rotor will try to catch the synchronous speed.
Yes.
Sir, and while explaining, you said that if it catches the synchronous speed, the rotors will slow down. It will
But
sleep. You explained that it will sleep like.
no. I never said like that. See, the rotor never runs with a speed equal to synchronous speed, right?
Yes, sir.
Now let me imagine that if the rotor rotates with synchronous speed, the torque will be zero, right?
Yes, sir.
When the torque is zero, the rotor will slow down. That is the general thing. But there is no chance that the rotor can run with synchronous speed. Why? You can have a clear picture when I'm talking about torque slip characteristics. There is no chance that it can run with a synchronous speed. If you connect the rotor to some external prime mover, and with the help of that external prime mover, you can make the rotor to rotate with synchronous speed. But by its own, there is no chance that it can run with a synchronous speed. It always runs with a speed less than synchronous speed. That difference we are calling it as a slip.
Okay, sir.
And
That was only my doubt. If it runs at synchronous speed, then it will slow down, and the speed will vary from synchronous to NR.
no,
That
no.
was my doubt.
So it never runs, right? So when not tomorrow, in the coming days, when I'm talking about torque slip characteristics, I'll stress more why it cannot run with synchronous speed. It will always run with a speed closer to ns. So one of the question has asked, sir, how it is been designed like that? Basing on the torque slip characteristics, it has been designed like this. So we are forcing the rotor always to rotate with the speed closer to ns. How we'll see that? Is it okay?
Okay, sir. Thank you, sir.
Right. See, one of the student has raised the questions in that question and answer. Sir, how it is being designed always with the speed closer to ns, basing on the torque slip characteristics. So whatever the machine we design, we have the torque slip characteristics in such a way that the speed should be closer to ns. What is that? I'll show it in the coming days. Don't worry. Just 1 or 2 days. Wait. Then I can explain to that answer. Right. Next.
Hello.
Pallavi. Pallavi.
Sir, I have doubt in today's starting phasor diagram.
Today's class.
Phasor
Yeah.
diagram. In that, sir, how the magnitude of E2 is less than E1. I didn't catch
Yeah.
it.
Yeah. Yeah. See, if the rotor is rotating with a speed of nr,
Yes.
what is the relative speed between field and the rotor conductors?
NS minus NR.
nr. The stator conductors
NR.
are ns minus nr, correct? The
Uh-huh.
stator conductors are stationary or rotating?
Stationary.
Then what is the relative speed?
NS minus NR.
ns minus 0.
Minus N. NS minus 2.
ns minus 0, correct?
At starting, yes.
Yeah. No. Stator is always stationary.
Yes, sir, but at starting rotor is not rotating. That's why NR is equals to 0, na, sir.
See. Okay.
Uh-huh.
So if I take the synchronous speed as 1000 rpm,
Okay.
then the rotor speed as 0.
Okay.
And then what is the relative speed between the stator field and the rotor? 1000, correct?
1000. Yes, sir.
Stator is stationary or rotating?
Stationary.
What is the relative speed?
NS.
ns, right? It is 1000 rpm in this case.
Yes, sir. Yes, sir.
But when the rotor starts rotating, what happened to the relative speed?
Also varying as
Decreases. It becomes
decrease.
right? If the rotor
NS minus
if the rotor speed is say 990, what is the relative speed?
10 only, na, sir.
10. So flux cuttings will be
Less.
EMF will be
Less.
But stator is always
Stationary.
relative speed is always
Relative
ns.
vary NS.
Then flux cuttings will be always maximum.
Maximum.
EMF will be always maximum. So that is the reason I have drawn E1 as a lengthy vector, E2 as a small vector. Is this clear, ma, Pallavi?
Yes, sir. Clear.
Right. Okay.
Thank you.
Right. So no one is raising the hands. I'm waiting. So Anil Kumar. Yeah, Anil Kumar.
Good
Malhotra.
evening, sir.
Good evening, Anil Kumar, please.
Sir, could you explain that series branches and branch are equal circuit?
See, the ohmic losses depends upon current or voltage.
So ohmic loss depend upon current, sir.
Current is a series parameter or shunt parameter.
Series parameters.
That is the reason it is a series branch, right?
Okay, sir.
The magnetic flux lines depends upon current or voltage.
So magnetic flux is current, sir.
Then current is a series parameter, shunt parameter.
Series parameter.
Then it is a series branch. Now clear, Anil?
Yes, sir. Yes, sir.
Right, right.
Thank you, sir.
Right. Still. Right. So no one is raising the hands. So it is clear then. I'll stop for today.